Imagine objects and particles in space that defy everything we know. There are dark matter and dark energy, strange forces that make up most of the universe, yet are completely invisible. We only know they exist because of how they affect the things we can see, like galaxies and light. And then there are fast radio bursts, sudden, intense signals from deep space that flash for milliseconds and then disappear, leaving scientists puzzled about their origin. Quasars are another mystery, supermassive energy sources that shine brighter than entire galaxies but are powered by unknown forces. Even stranger are rogue planets, drifting alone in space without a star. These nomads could hold secrets about how planets form. And let's not forget the possibility of other dimensions or particles we can't yet detect, like axions or gravitons, which might rewrite the rules of physics altogether. Each discovery opens the door to more unknowns, proving that the universe still holds secrets beyond our imagination. Join us today as we uncover the universe's most mysterious objects. As we peer into the vast expanse of our universe, we encounter celestial objects that challenge our understanding and ignite our curiosity. One such fascinating discovery is the pulsar. These rapidly spinning neutron stars emit beams of radiation from their magnetic poles, which sweep across space like lighthouse beams. What makes them especially enigmatic is their precision. Some pulsars spin hundreds of times per second, creating remarkably regular signals, akin to the ticking of a cosmic clock. Another remarkable category of celestial wonders is black holes. While most people associate black holes with the idea of something dark and mysterious, they are actually regions in space where gravity's pull is so strong that nothing, not even light, can escape. The very existence and characteristics of black holes, especially supermassive ones found at the centers of galaxies, provoke profound questions about how they form and influence their surroundings. Recent discoveries involving the merging of black holes via gravitational waves have opened new avenues of inquiry, reshaping our conception of the universe itself. Then, there are quasars, the luminous cores of distant galaxies powered by supermassive black holes. Faint and exceedingly distant, quasars can outshine entire galaxies when they are actively consuming material. Their brightness and distance make them not only extraordinary in themselves, but also valuable tools for astronomers. Studying them helps us understand the early universe, as they can be seen across vast cosmic timescales. Lastly, we encounter rogue planets, planets that wander alone through the galaxy without a parent star. These intriguing bodies challenge our ideas about planetary formation and stability. With estimates suggesting there could be billions of rogue planets in our galaxy alone, they may hold secrets about the dynamics of planetary systems, gravitational influences, and perhaps even conditions that could support life, far removed from their solar origins. Each of these unusual celestial objects offers not only wonder, but also deep insights into the mysteries of our universe. Rogue planets, those mysterious celestial bodies that drift through the galaxy without being bound to any star, present intriguing challenges to our understanding of planetary formation and behavior. Traditionally, we viewed planets as objects tethered to stars, forming from the same swirling disks of gas and dust that create stellar systems. But the existence of rogue planets suggests a more complex narrative, indicating that not all planets follow this neat origin story. One of the most fascinating aspects of rogue planets is how they might form. Some theories propose that these planets could be ejected from their original star systems due to gravitational interactions. This means that a planet may start its life in a stable orbit around a star, but due to the chaotic dynamics of multiple bodies, it can be flung into the interstellar void. This challenges conventional models of planetary formation, as it implies there are more dynamic processes at play in the cosmos than we had previously understood. Moreover, rogue planets challenge our perspective on what a planet is. With no sunlight to warm them, these free-floating worlds rely on internal heat sources, such as radioactive decay, to sustain any potential atmospheres or perhaps even subsurface oceans. This presents the possibility of entirely new ecosystems that could exist in complete darkness, expanding our definition of habitability and life beyond the conventional confines of star-bound planets. The existence of rogue planets also hints at the vastness of celestial diversity. As we discover more of these wandering worlds, we are prompted to reevaluate our theories and assumptions about planetary behavior. There's a whole universe that still eludes us, reminding us that in our quest to understand the cosmos, the reality is often stranger than the theories we create. Each rogue planet we find not only enriches our knowledge, but also ignites our curiosity about how many more secrets the universe holds. Neutron stars are among the most fascinating celestial objects in our universe, formed from the remnants of massive stars that have undergone supernova explosions. When these larger stars exhaust their nuclear fuel, they collapse under their own gravity. The intense pressure causes protons and electrons to combine, resulting in a mass mostly composed of neutrons. These remnants are incredibly small, typically no wider than a city, yet they encapsulate a remarkable amount of mass, squeezing more than 1.5 times the mass of our Sun into a sphere the size of about 20 kilometers across. One of the defining characteristics of neutron stars is their extraordinary density. To put this into perspective, just a sugar cube-sized amount of neutron star material would weigh approximately 600 million tons. This means that their core density can exceed the density of an atomic nucleus. Such density arises from the strong nuclear forces that dominate at microscopic scales, tightly packing neutrons together beyond the usual limits found in ordinary matter. Neutron stars also possess incredibly strong magnetic fields, potentially 1 trillion times stronger than Earth's. These magnetic fields can lead to a variety of phenomena, such as pulsars, which are rotating neutron stars that emit beams of radiation. As these beams sweep across space, they may be detected as regular pulses, akin to a cosmic lighthouse. This characteristic allows scientists to study neutron stars and gain insight into not only their structure, but also the fundamental physics of matter under extreme conditions. Further adding to their mystique are the exotic states of matter believed to exist within neutron stars. At their centers, matter may reach states that current theories can only speculate about, including superfluidity and perhaps even quark-gluon plasma. This potential for new physics makes neutron stars not just dense but also fundamentally interesting to astrophysicists, exploring the boundaries of our understanding of the universe. As we peer into the cosmos, these stellar remnants serve as crucial laboratories, revealing secrets about the fundamental nature of matter and the extremes of gravitational forces. Quasars, or quasi-stellar objects, are among the most enigmatic phenomena in the universe. They are incredibly bright and distant objects, believed to be powered by supermassive black holes at the centers of galaxies. As matter spirals into these black holes, it becomes heated to extreme temperatures, emitting intense radiation across the electromagnetic spectrum. This process results in their incredible brightness, often outshining entire galaxies. The sheer energy emitted by quasars allows astronomers to study the universe's early stages, giving us valuable insights into a time when galaxies were still forming. What makes quasars particularly intriguing is their distance from Earth. Many of the quasars we observe today are billions of light-years away, meaning we are looking back in time. Because light travels at a finite speed, observing these distant quasars allows us to peek into the universe's past, revealing the conditions and environments that existed when galaxies were younger. This perspective is crucial for understanding the evolutionary history of the cosmos. In fact, some quasars formed less than 1 billion years after the Big Bang, illustrating how rapidly the first black holes and galaxies gathered mass and energy in the early universe. Additionally, the light from quasars can be affected by the material it travels through, such as gas and dust in the intergalactic medium. This interaction provides researchers with clues about the composition and density of the universe during its formative years. By studying the spectra of quasar light, scientists can determine the presence of elements and trace the distribution of matter across vast distances. This knowledge helps to build a clearer picture of how galaxies evolved and how they interacted with their environment long ago. Quasars serve as cosmic beacons, illuminating the vast canvas of space and time. They not only challenge our understanding of black holes and cosmic evolution, but also encourage us to ponder the origins of the universe itself. The mysteries surrounding quasars continue to captivate astronomers, who leverage these extraordinary phenomena to unlock the secrets of the cosmos. Dark matter plays a crucial role in our understanding of galaxies and how they form. Invisible and undetectable through traditional means, dark matter does not emit light or energy. However, its presence is inferred from its gravitational effects on visible matter. This has led astronomers to conclude that dark matter is a fundamental component of the universe, making up approximately 85% of all matter. As a result, it significantly influences the structures and behaviors of galaxies. One key implication of dark matter is the way it shapes the formation of galaxies. The leading theory suggests that dark matter formed clumps in the early universe, creating gravitational wells. These wells attracted normal matter, primarily gas and dust, leading to the birth of stars and galaxies. Without dark matter, galaxies would not have enough gravitational pull to hold onto their mass, resulting in a very different cosmic landscape, one where the universe would appear less clustered and rich in galactic formations. Additionally, dark matter helps explain the motion of galaxies within clusters. Observations have revealed that galaxies are moving much faster than expected based solely on the amount of visible matter. This discrepancy led to the conclusion that unseen mass, in the form of dark matter, must be present to account for the additional gravitational pull. This understanding has significantly changed the way we look at galaxy interactions and dynamics, revealing that these cosmic bodies are not merely collections of stars, but also complex ecosystems influenced by unseen forces. As our telescopes and technology improve, we continue to probe the mysteries of dark matter. Investigating its role strengthens our understanding of cosmic evolution. Essentially, dark matter serves as a cosmic scaffolding, crucial for the formation and maintenance of the structures we observe in the universe today. In doing so, it reshapes not only our knowledge of galaxies, but also our fundamental perceptions of the cosmos itself. The Milky Way is a barred spiral galaxy, which means it has a central bar-shaped structure made of stars, with spiral arms radiating outward. This design distinguishes it from other galaxy types, like elliptical galaxies that lack the distinct features of spiral arms. In many ways, our galaxy's structure is a symphony of hundreds of billions of stars, interstellar gas, and dust, all held together by gravity, creating a vibrant and dynamic environment that puzzles astronomers. One of the defining characteristics of the Milky Way is our position within it. We reside in one of its spiral arms, known as the Orion Arm, located about 28,000 light-years from the galactic center. This center can be a mysterious place, home to a supermassive black hole named Sagittarius A star. This black hole, with a mass millions of times that of our Sun, draws in matter and releases immense energy, yet its workings are not entirely understood, making it a subject of intense study. The Milky Way also has a complex halo of stars and globular clusters that envelop it. This halo is filled with dark matter, a substance that makes up a significant portion of our galaxy's total mass but remains invisible to us. The presence of dark matter raises questions about our galaxy's formation and evolution, as scientists work to unravel how it interacts with visible matter. Exploring the Milky Way's dark halo can provide vital clues about gravitational forces and cosmic history. Another of the galaxy's unique mysteries lies in its ongoing formation and evolution. The Milky Way has absorbed smaller galaxies over time, which has shaped its current structure. Each instance of galactic merging adds new stars and alters the dynamics of the galaxy. As we observe these processes, we gain insights into the fate of the Milky Way. Will it continue to grow larger by merging with neighboring galaxies, or will it eventually collide with the Andromeda galaxy? The journey of the Milky Way continues to captivate and inspire curiosity about our place in the universe. The Andromeda galaxy, our closest large galactic neighbor, sits approximately 2.5 million light-years away from Earth. Its stunning spiral shape contains an estimated 1 trillion stars, far surpassing our Milky Way's population. Among its many intriguing features, Andromeda is renowned for its impressive size, making it one of the largest galaxies in our local group. This spiraling collection of stars and cosmic matter also boasts a complex structure, including numerous star clusters and bright nebulae, some of which give birth to new stars while others contain remnants of exploded stars. This spiraling collection of stars and cosmic matter also boasts a complex structure, including numerous star clusters and bright nebulae, some of which give birth to new stars while others contain remnants of exploded stars. Andromeda is also famous for possessing two smaller companion galaxies, M32 and M110. These dwarf galaxies orbit Andromeda and provide scientists with insights into how galaxies interact with one another. The gravitational dance between Andromeda and these companions influences their shapes and star formation rates. Additionally, observations reveal that Andromeda has a supermassive black hole at its center, much like its counterpart in the Milky Way, which fuels the galaxy's dynamic behaviors. Looking toward Andromeda's future, scientists predict a monumental event. A collision with the Milky Way is anticipated in about 4 billion years. This collision will not be a catastrophic event as one might imagine. Instead, our galaxies will likely pass through each other, with their vast distances preventing most stars from colliding. However, the gravitational forces will stir both galaxies, triggering waves of star formation and creating a spectacular new galactic structure that is often referred to as Milkomeda or Milkdromeda. These predictions offer a glimpse into the dynamic nature of galaxies and remind us of the ever-changing cosmos around us. As we gaze at Andromeda today, we're witnessing not only its present state, but also a glimpse into its storied past and an exciting future that is yet to unfold. The wonders of the universe continue to unfold, inviting us to explore and understand the secrets that lie beyond our home in the Milky Way. Colliding galaxies are not just spectacular cosmic events, they are key to understanding the evolution of our universe and the mysteries of cosmic matter. When two galaxies collide, they interact in complex ways, leading to a variety of phenomena that reveal the intricate processes shaping galaxies over billions of years. For instance, these collisions can spark bursts of star formation as clouds of gas and dust are compressed. This activity allows astronomers to witness the birth of new stars in a matter of millions of years, providing a living laboratory to study stellar evolution. Moreover, observing colliding galaxies helps scientists decode the composition of cosmic matter. As galaxies merge, they bring together their stars, gas, dust, and even dark matter. The interactions alter their structures and dynamics, offering clues about how different forms of matter influence galaxy behavior. Instruments like radio telescopes and optical observatories can capture a wide range of emissions from these galaxies, revealing the presence of elements and compounds that tell us about the building blocks of the cosmos. These grand collisions also challenge our understanding of dark matter, which makes up a significant part of the universe, yet remains elusive. As galaxies interact, the gravitational influence of dark matter can be observed indirectly through the behavior of visible matter. Studying these gravitational effects helps refine our models of how dark matter contributes to galaxy formation and growth over time. Finally, the significance of colliding galaxies extends beyond mere observation. They set the stage for understanding the future of our own Milky Way. In approximately 4 billion years, our galaxy is expected to collide with the Andromeda Galaxy, a cosmic event that will reshape both galaxies profoundly. By studying current galactic collisions, we can better prepare for this eventual merging, making us not only spectators of the universe's history, but also part of its unfolding story. Supermassive black holes are colossal entities often found at the centers of galaxies, holding masses equivalent to millions or even billions of our Sun. Their existence and influence on galaxy formation are intertwined, forming a pivotal part of our cosmic narrative. When galaxies began coalescing after the Big Bang, gas and dust underwent gravitational collapse, with some regions forming dense cores, eventually evolving into stars and, in time, primitive galaxies. It's in these environments that supermassive black holes start their journey. As galaxies formed, they accumulated matter, and within this turbulent environment, black holes grew through two primary mechanisms: the merging of smaller black holes and the accretion of gas and stars. When two galaxies collide, their central black holes can also merge, creating an even more massive black hole in the aftermath. Additionally, gas falling into these black holes can unleash immense amounts of energy, which produced powerful jets and radiation, influencing star formation in the surrounding regions. This process can regulate the growth of the galaxy, helping to carve out space for new stars while simultaneously reshaping the galaxy's structure. Moreover, supermassive black holes can act like cosmic traffic lights. When they unleash energy in the form of radiation and jets, they can heat the surrounding gas, preventing it from cooling and collapsing to form new stars. This feedback mechanism plays a critical role in determining how galaxies evolve over time. If a black hole becomes particularly active, it can effectively inhibit the star formation in its host galaxy, leading to what we observe in many older galaxies today, a decreased rate of new star creation. Ultimately, the interplay between supermassive black holes and galaxies is a delicate dance of creation and destruction. They are not merely bystanders in the cosmic story. Instead, they drive the evolution of galaxies, shaping their growth, structure, and longevity. As we delve deeper into the universe, understanding these titanic forces within our celestial neighborhoods promises new revelations about the cosmos and our place within it. Irregular galaxies, distinct for their chaotic shapes and lack of symmetry, have become valuable subjects in the study of cosmic evolution. Unlike spiral or elliptical galaxies, irregular galaxies often exhibit a mix of stars, gas, and dust with no defined structure. This unique characteristic allows scientists to explore the processes that lead to galaxy formation and growth. By examining these galaxies, researchers gain insight into how gravity, stellar wind, and interactions within galactic clusters contribute to the complex tapestry of the universe. One of the most intriguing aspects of irregular galaxies is their youth relative to other galaxy types. Many irregulars seem to be in the early stages of galactic development, offering a glimpse into the processes that may have shaped the early universe. Through studying their star formation rates, scientists can identify how rapidly stars are being born in these galaxies, shedding light on the environmental conditions conducive to star formation. The presence of heavy elements or metals in these galaxies also provides clues about previous generations of stars and their life cycles, revealing the historical context of galaxy evolution. Moreover, irregular galaxies often show signs of interactions with other galaxies. These interactions can trigger bursts of star formation and prompt a rearrangement of stellar material. By observing how these galaxies respond to gravitational forces or collision events, scientists can draw conclusions about the role of external influences in shaping a galaxy's trajectory. This line of inquiry helps explain why galaxies can appear so different and reinforces the idea that galactic evolution is a dynamic, ongoing process rather than a linear one. The study of irregular galaxies has opened fresh avenues for understanding the universe's history. As researchers delve deeper into these enigmatic celestial bodies, they uncover the intricate interplay of cosmic forces that drives evolution, ultimately piecing together a broader narrative of how galaxies and the universe itself have evolved over time. Through this lens, we can appreciate the rich and varied landscape of our cosmos, which continues to surprise and inspire. Gamma-ray bursts are among the most spectacular and powerful events that occur in our universe. They are intense flashes of gamma rays, which are the highest energy form of light. These bursts are so powerful that they can outshine entire galaxies for brief periods, releasing more energy in a few seconds than our sun will emit over its entire lifetime. Two primary theories explain the origins of gamma-ray bursts. The first involves the collapse of massive stars, specifically those with a mass greater than 20 times that of our Sun. When such a star exhausts its nuclear fuel, it can no longer support itself against gravitational collapse. This collapse leads to a supernova event, and in its aftermath, the formation of a black hole can occur. The energy from the collapsing core can produce jets of particles that move at nearly the speed of light, emitting gamma rays as they interact with surrounding material. The second theory suggests that gamma ray bursts can also stem from the collision of neutron stars. Neutron stars are remnants of supernova explosions and are incredibly dense. When two neutron stars orbit one another and eventually collide, the immense gravitational forces can create powerful shockwaves, resulting in a gamma ray burst. This scenario sheds light on the potential for these breathtaking events to happen in dense regions of the universe, like galaxies where neutron stars might congregate. What makes gamma ray bursts so extraordinary is not just their intensity, but also their brevity. They typically last from a fraction of a second to several minutes, but during that time they release more energy than our sun will emit over its entire existence. This level of energy places gamma ray bursts among the most energetic events known to science. Understanding these phenomena not only provides insight into the life cycles of stars and the nature of black holes and neutron stars, but also expands our knowledge of the universe's most extreme processes. Gravitational lensing is a fascinating phenomenon that occurs when a massive object, like a galaxy or cluster of galaxies, bends the light from a more distant object behind it. This bending happens due to gravity, which can distort our perception of the actual distances and sizes of celestial bodies. Instead of seeing a straight line from one star to another, light curves around the massive object, creating multiple images, rings, or arcs of the light source. This effect can significantly alter how we measure astronomical distances. When astronomers observe distant galaxies that are being lensed, they might initially calculate the distance based on their position in the sky. However, the lensing object alters these apparent positions and can amplify or diminish the brightness of the background galaxies. As a result, what we perceive in the night sky may not accurately reflect the true distances between objects, leading to potential misunderstandings of the universe's structure. Furthermore, gravitational lensing allows scientists to study objects that would otherwise be too faint to detect. By observing how light from these distant sources is distorted, astronomers can infer information about the mass and distribution of the lensing object. This has opened up new avenues for exploring dark matter, which doesn't emit light but exerts gravitational influence. The lensing effect provides a unique perspective on how much unseen mass there is in the universe, enhancing our understanding of cosmic evolution. Ultimately, gravitational lensing challenges our traditional views about the universe. It compels us to reconsider the scale, size, and distances of celestial objects and pushes the boundaries of our astronomical understanding. Each observation not only offers a glimpse into distant worlds, but also highlights the intricate workings of gravity and light in shaping our cosmic perception. The Fermi paradox presents an intriguing question. If there are so many stars in the universe, and many of them likely host planets, why have we not yet encountered any signs of intelligent extraterrestrial life? This contradiction between the high probability of alien civilizations and the lack of evidence has sparked numerous theories and discussions among scientists and astronomers. One leading theory is known as the rare Earth hypothesis. This viewpoint suggests that while microbial life might be common in the universe, the conditions necessary for complex intelligent life are extremely unique to Earth. Factors such as a stable climate, the presence of a large moon, and the protective nature of gas giants like Jupiter play a crucial role in making Earth suitable for advanced life. Without such a perfect mix of conditions, intelligent life may be exceedingly rare. Another possibility is the concept of the Great Filter. This theory proposes that there is a stage in the evolution of life that is incredibly difficult for species to surpass, whether that be the emergence of life itself, the transition from single-celled to complex organisms, or the development of civilizations that can communicate across interstellar distances. If this great filter is ahead of us, it might indicate an impending downfall for intelligent species, including our own. Alternatively, if it lies behind us, it could mean we are one of the very few, if not the only, intelligent civilizations to have made it to this point. These theories reveal that the search for intelligent life is not just a quest for the unknown, but also a reflection on our own existence and the fragile nature of life in the cosmos. Each idea invites us to ponder our place in the universe, the uniqueness of Earth, and the potential futures that await us as we continue to explore the stars. As we expand our horizons and technologies, the question may evolve, but the curiosity to understand whether we are alone in the vastness of space remains a fundamental aspect of our scientific journey. The atmospheres of Venus and Titan, both remarkable and distinctly different from Earth's, offer fascinating insights into planetary climate evolution. Venus, often referred to as Earth's sister planet, possesses a thick atmosphere made primarily of carbon dioxide, with clouds laden with sulfuric acid. The extreme greenhouse effect on Venus results in surface temperatures soaring above 400 degrees Celsius, far exceeding those found on Earth, even in its hottest deserts. Studying Venus helps scientists understand how a runaway greenhouse effect can drastically alter a planet's climate. In contrast, Titan, Saturn's largest moon, has a nitrogen-rich atmosphere that is eerily similar to Earth's in terms of its primary components. However, it is much colder, with surface temperatures around -180 degrees Celsius. Titan hosts methane clouds, rain, and rivers of liquid methane. This unique dynamic indicates a different kind of greenhouse effect, one that offers clues about the behavior of hydrocarbons in cold environments and the potential for complex chemical processes that could occur in different climates over time. By examining the atmospheric dynamics of these two celestial bodies, scientists glean valuable information about atmospheric composition, pressure, and temperature. The processes that dominate on Venus, like its thick cloud cover leading to intense surface heat, contrast sharply with Titan's methane cycle, where ethereal clouds and liquid lakes shape its landscape. Such analyses help researchers understand the consequences of different atmospheric conditions and how they can lead to divergent evolutionary tracks for planetary climates. Moreover, these peculiarities highlight the importance of a planet's distance from the Sun, its atmospheric makeup, and its surface conditions. The lessons learned from Venus and Titan not only intrigue scientists, but also serve as warnings, reflecting how subtle differences can lead to vastly different climate outcomes. By piecing together the atmospheric puzzles of these worlds, we gain a deeper appreciation of the delicate balance that governs climate, both in our own world and beyond. Fast radio bursts, often abbreviated as FRBs, are brief yet intense bursts of radio waves that originate from deep space. They were first discovered in 2007, but their significance has only grown as astronomers identify them as one of the most fascinating anomalies in astrophysics. What makes FRBs particularly intriguing is their duration. They typically last just a few milliseconds, but during that time, they emit more energy than our Sun does in an entire day. This immense output raises questions about the astrophysical processes behind them. The origins of FRBs are largely shrouded in mystery, adding to their allure. Although researchers have tracked some of these bursts back to specific galaxies, others remain untraceable. This uncertainty stems from their sporadic nature. Some FRBs occur once and then never again, leading scientists to ponder whether they are caused by a range of cosmic phenomena, such as exploding stars, neutron stars, or even more exotic theories involving dark matter or extraterrestrial technology. The variability in their characteristics complicates matters further, underlining our limited understanding of their underlying mechanisms. Another reason for the mystery surrounding FRBs is their detection. Most observatories that study the night sky are equipped to analyze signals from specific frequencies. However, FRBs can occur across a broad range of wavelengths, and due to their fleeting nature, they may go unnoticed. As our technology improves, we're starting to better capture these puzzling bursts, but this often means our understanding lags behind the sheer number of FRBs observed. In fact, every new detection seems to invite further questions rather than answer existing ones. Ultimately, the significance of fast radio bursts goes well beyond the need to understand their origins. They serve as cosmic messengers, potentially carrying clues about the conditions in distant galaxies, the nature of space-time, and even the fundamental workings of the universe. As researchers continue to unravel these intriguing signals, each new discovery pushes the boundaries of our knowledge and deepens our curiosity about the cosmos around us. Exoplanets, or planets beyond our solar system, capture our imagination, especially those found in the habitable zone. The habitable zone, often referred to as the Goldilocks zone, is the region around a star where conditions are just right for liquid water to exist on a planet's surface. This is crucial because water is considered one of the primary ingredients for life as we know it. It's neither too hot nor too cold, allowing for the possibility of nurturing various chemical reactions essential for life. These planets often have certain defining features. Typically, they are rocky, similar to Earth, which provides the necessary geological framework for supporting life. The size of these exoplanets is also significant. Those comparable in size to Earth have a better chance of retaining their atmospheres, which play a vital role in shielding the surface from cosmic radiation and aiding in temperature regulation. An atmosphere rich in gases could be crucial for sustaining any potential life forms, as it can lead to processes such as weather patterns and the cycling of nutrients. Moreover, the type of star these planets orbit also matters. Stars similar to our Sun, which provide a stable energy output over billions of years, create a more promising environment for life. Some exoplanets are found in multi-planet systems, which may further enhance the conditions for life by facilitating interactions that could lead to complex environments. The study of these environments helps scientists broaden their understanding of planetary formation and the diverse possibilities that life may emerge under. The search for extraterrestrial life is greatly inspired by the discovery of exoplanets in the habitable zone. Each finding encourages scientists to explore these distant worlds more deeply. Missions that focus on characterizing their atmospheres, surface conditions, and potential biosignatures, the chemical indicators of life, are underway. As we probe into these hopeful invitations from the cosmos, we are not just searching for life, we are also reflecting on our own existence and the unique processes that led to life on Earth. Each new discovery adds another piece to the puzzle of our place in the universe, inviting us to imagine what life, if it exists elsewhere, might be like. Gas giants like Jupiter and Saturn hold a unique and critical position in our understanding of planetary systems. These colossal planets, predominantly made of hydrogen and helium, differ vastly from terrestrial planets like Earth and Mars. Their immense size and mass shape not only their own characteristics, but also influence the structure and evolution of their entire solar systems. One of the most striking aspects of these gas giants is their atmosphere, which displays a fascinating array of weather patterns and phenomena. Jupiter, for instance, is home to the Great Red Spot, a storm larger than Earth that has raged for centuries. This dynamism in their atmospheres provides insights into atmospheric sciences, with models developed for these distant worlds often helping us interpret our weather systems back home. Additionally, the magnetic fields generated by these gas giants are hugely significant, showing how such forces can affect surrounding celestial bodies. Moreover, the moons orbiting these giants expand our understanding of the potential for life beyond Earth. Jupiter's moon Europa possesses a subsurface ocean beneath its icy crust, raising questions about the conditions for life elsewhere in the universe. Saturn's moon Titan, with its dense atmosphere and surface lakes of liquid methane, provides an entirely different angle on what habitats might exist. These moons serve as natural laboratories, helping scientists hypothesize about the diversity of life forms that could thrive in extraterrestrial environments. Lastly, gas giants play a pivotal role in the formation of planetary systems. They can clear out debris, influencing where and how terrestrial planets form. Their gravitational influence helps shape the orbits of other celestial bodies, lending critical insight into the dynamics of whole solar systems. By studying Jupiter and Saturn, we not only learn about our own neighborhood in space, but also gain a broader understanding of the myriad planetary systems scattered throughout the universe. Icy moons such as Europa and Enceladus are captivating to scientists exploring the potential for life beyond Earth. Both moons harbor vast oceans beneath their icy crusts, creating environments that might support life. Europa, one of Jupiter's largest moons, has a surface covered in thick ice, but beneath this frozen layer lies a saltwater ocean, possibly twice as deep as Earth's oceans. This ocean is kept warm through heat generated by gravitational interactions with Jupiter, suggesting conditions that could be suitable for life. Enceladus, a smaller moon orbiting Saturn, shares similar intrigue. In recent years, the Cassini spacecraft revealed geysers of ice and water vapor spewing from its southern polar region. Analysis of these plumes showed they contain organic molecules, which are the building blocks of life. The presence of water, coupled with these organic compounds and the potential for geothermal activity, makes Enceladus a strong candidate in the search for extraterrestrial life. The significance of these findings is profound. Scientists believe that where there is liquid water, there is a possibility of life. The environments found in both Europa and Enceladus mirror those we see in extreme conditions on Earth, such as hydrothermal vents in deep oceans. Some microorganisms on our planet thrive in these harsh environments, raising the tantalizing possibility that life could exist in similar niches elsewhere in our solar system. As missions to study these enigmatic moons are planned, such as NASA's Europa Clipper and the proposed mission to Enceladus, the excitement continues to grow. These explorations may not only reveal the secrets of icy moons, but could also expand our understanding of life's potential diversity throughout the universe. In every icy surface that hides a watery ocean, there lies a frontier of tantalizing possibilities waiting to be uncovered. In the vast tapestry of the universe, researchers have made incredible strides in understanding the atmospheres of exoplanets, those tantalizing worlds orbiting stars beyond our solar system. One of the most groundbreaking discoveries has been the detection of unexpected atmospheric compositions on planets that seem radically different from our own Earth. For instance, some exoplanets, previously thought to be inhospitable, have shown signs of chemical compounds like water vapor and even clouds, hinting at possible climate systems. This realization challenges the long-held assumption that life-sustaining environments must closely mirror our own. Take the case of the so-called hot Jupiter exoplanets, gas giants that orbit extremely close to their stars. Astronomers have found that some of these planets boast thick atmospheres rich in metals and other elements, which is something entirely foreign to our experiences on Earth. The measurement of sodium and potassium in these hostile environments raises questions about how we define habitability. The presence of such elements suggests complex atmospheric dynamics, which were previously unforeseen in contexts defined strictly by our terrestrial norms. Moreover, the recent advancements in technology, like the James Webb Space Telescope, have ushered in a new era of discoveries. With its advanced capabilities, scientists have been able to capture spectra that reveal the unique fingerprints of molecules within these distant atmospheres. For example, observations made by the telescope have confirmed the presence of carbon dioxide and even hints of methane on some exoplanets. These findings not only expand our understanding of what constitutes an atmosphere, but also compel us to reconsider our criteria for potential life elsewhere in the universe. As we stand on the precipice of these discoveries, it becomes increasingly clear that the universe is filled with a diverse array of worlds, each with its own unique atmospheric conditions. These revelations challenge our Earth-centric viewpoint and spark wonder about the potential for life on planets that were once dismissed as barren. Our quest for knowledge about these distant atmospheres opens a fascinating dialogue about what we might discover, emphasizing that the truth about life's potential beyond Earth may be more complex and varied than we have ever imagined. The study of retrograde orbits, where a planet or moon orbits in the opposite direction to the rotation of its parent body, offers fascinating insights into the history and evolution of planetary systems. These unusual orbits can hint at a tumultuous past, suggesting that the formation of a planetary system may have involved violent interactions, such as collisions with other celestial bodies or gravitational disturbances from nearby stars or objects. One important feature of retrograde orbits is their tendency to occur more frequently with smaller bodies or moons. For instance, several of Jupiter's moons, like Triton, exhibit retrograde motion. This scenario often indicates that these moons might not have formed in place. Instead, they could have been captured from different regions of the solar system or might have originally been part of another system, whose trajectory was altered during a close encounter. Such capture scenarios help astronomers piece together the dynamic and often chaotic processes that govern planet formation. Moreover, examining retrograde orbits sheds light on the gravitational influences exerted by other planets. For example, the gravitational tug of a large gas giant can destabilize the orbits of smaller bodies, leading to orbital migrations. These interactions can result in a mix of prograde and retrograde orbits within a single system. Understanding the circumstances that led to the development of these orbits can inform us about the formation conditions and the evolutionary paths different planetary systems may take, but also about the behavior and interactions within developing systems. These insights enrich our understanding of the cosmos and the evolutionary narratives that shape the worlds we observe today. The theory of the expanding universe has gathered significant support through several key observations. One of the most compelling pieces of evidence comes from the work of astronomer Edwin Hubble in the early 20th century. Hubble discovered that distant galaxies are moving away from us, and the farther a galaxy is, the faster it appears to be receding. This observation led to the formulation of Hubble's law, which indicates that the universe is not static, but is continuously expanding. This expansion is further substantiated by the cosmic microwave background radiation. Discovered in the mid-20th century, this faint glow fills the universe and is a remnant of the early hot stages of the cosmos shortly after the Big Bang. The uniformity and slight fluctuations in this radiation offer insights into the universe's early conditions, supporting the idea that it has been expanding ever since those formative moments. The implications of this expansion are profound for our understanding of space and time. It alters our perception of the cosmos, suggesting that what we see in the night sky is not a static arrangement of stars and galaxies, but a dynamic landscape that has been changing and evolving over billions of years. The expansion implies that space itself is stretching, and as a result, distances between galaxies increase, shaping our view of the universe as a complex and ever-evolving system. Moreover, this understanding influences how we think about the future of the universe. The expansion could continue indefinitely, suggesting scenarios where galaxies drift apart forever, leading to a colder, darker cosmos in the distant future. Conversely, theories like the Big Crunch or Big Rip propose different end states depending on the behavior of dark energy, a mysterious force that drives this expansion. Each of these possibilities invites us to ponder the fate of all that exists, reminding us of the vastness and complexity of the universe we inhabit. Cosmic inflation is a fascinating theory that offers a compelling explanation for the uniformity we observe in the universe today. According to this concept, shortly after the Big Bang, the universe underwent an extremely rapid expansion, growing exponentially in a fraction of a second. This inflationary period spread the fabric of space itself, smoothing out any irregularities and causing distant regions of space to become remarkably uniform. Before inflation, the universe was hot, dense, and full of tiny fluctuations. When inflation took hold, it amplified these fluctuations and stretched them across vast distances, essentially wiping the slate clean. As the universe continued to expand, these tiny variations were preserved, and when the universe cooled down, they eventually led to the formation of galaxies and larger structures we see now. This smoothing effect accounts for why the cosmic background radiation, which is the afterglow of the Big Bang, looks almost the same in all directions. Inflation also helps to explain the isotropy and homogeneity of the universe, two key properties we observe. Isotropy means that the universe looks the same regardless of the direction from which we observe it, while homogeneity indicates that the universe is similarly distributed when viewed on a large enough scale. Without inflation, it would be challenging to account for this uniformity, especially given the vast distances and the varying densities of matter throughout the universe. Cosmic inflation serves as a bridge linking the extremely high energy state of the early universe to the vast, complex universe we inhabit today. It offers us a way to understand not just the uniformity of the universe, but also the fundamental processes that continue to shape its evolution. The implications of this theory are profound, reminding us of the intricate dance of forces at play in the cosmos, guiding matter and energy through time and space. Dark energy is a mysterious force that makes up about 70% of the universe and is responsible for its accelerated expansion. This discovery has profound implications for the fate of the cosmos. As the universe continues to expand at an increasing rate, dark energy suggests that galaxies will drift apart further over time. This may lead to a cold, dark, and empty universe, a scenario often referred to as the Big Freeze. In this future, stars will eventually burn out, and galaxies will become isolated, leaving an almost barren expanse. The significance of dark energy lies not only in its role in cosmic expansion, but also in the many questions it raises. Scientists have yet to ascertain its true nature. Some theories propose that dark energy is a constant energy density that fills space uniformly, while others suggest it could vary over time or be linked to the fundamental properties of space itself. This uncertainty has sparked heated debates among scientists as they grapple with how to integrate dark energy into our understanding of physics. One of the intriguing aspects of this discussion is how dark energy challenges existing frameworks. Traditional gravity, as described by Isaac Newton and later refined by Albert Einstein, works on the premise that the gravitational influence of mass attracts rather than repels. The introduction of dark energy disrupts this long-standing view, compelling researchers to rethink fundamental principles. Some speculate that understanding dark energy might even lead to discovering new physics beyond our current theories. As we continue to explore the cosmos, the implications of dark energy remind us of the limits of our understanding. Each new discovery in cosmic evolution tells us that we live in a dynamic and ever-changing universe. The enigma of dark energy thus serves as a powerful call to action for scientists, inviting them to unravel one of the most captivating mysteries of our time and refine our comprehension of the universe's ultimate fate. The distribution of galaxies across the universe paints a fascinating picture of the cosmic web, a vast, interconnected network of structures that grows from the forces of gravity and dark matter. Galaxies are not scattered randomly. Instead, they tend to form in clusters and filaments, creating a complex tapestry that reveals the underlying architecture of our universe. This structure is crucial to understanding how matter has evolved since the Big Bang, providing insights into the formation of galaxies themselves as well as the nature of dark matter. When astronomers study maps of galaxy distributions, they notice that galaxies often align along invisible highways known as filaments. These filaments are essentially the strands of the cosmic web, connecting clusters of galaxies and forming large voids in between. The densest regions contain the most galaxies, while the vast voids have comparatively few. By analyzing these patterns, scientists can glean information about how matter has been influenced by gravitational forces over billions of years, which also helps explain the growth and evolution of structures in the universe. This distribution tells us more than just where galaxies are located. It also offers clues about the early universe and the conditions that led to the formation of structures we see today. Observing the cosmic web allows researchers to test theories regarding how dark matter interacts with regular matter, as most of the universe is believed to be composed of this elusive substance. Importantly, understanding these distributions can help refine our models of cosmic evolution and enhance our knowledge of fundamental physics. The cosmic web is like a vast, three-dimensional tapestry, revealing not just the current state of the universe, but also hinting at its history and future. As we continue to explore and map these cosmic structures, we deepen our understanding of the universe's fundamental nature. This journey allows us to connect with our cosmic origins, a perspective that has profound implications for our place in the universe. The cosmic microwave background radiation, often shortened to CMB, is a fascinating relic from a time when the universe was still in its infancy. It emerged about 380,000 years after the Big Bang, at a time known as the recombination epoch. Before this, the universe was a hot, dense soup of particles, making it opaque. As it expanded and cooled, protons and electrons began to combine to form hydrogen atoms, allowing light to travel freely for the first time. This light is what we now detect as the CMB. The CMB provides scientists with a snapshot of the universe in its earliest days. It is like a cosmic photograph taken at a pivotal moment in history. This radiation fills the entire universe and is remarkably uniform, but it also contains slight variations in temperature. These fluctuations are crucial because they reveal the density differences that led to the formation of galaxies and large-scale structures we see today. By analyzing these patterns, researchers can glean insights into the conditions and processes that shaped the early universe. In addition to teaching us about the early universe, the CMB offers clues about fundamental properties of our cosmos. For instance, it helps us understand the rate of expansion of the universe. Through detailed studies of the CMB's temperature fluctuations, scientists have been able to estimate various parameters such as the age of the universe, which is about 13.8 billion years, and the amount of dark matter and dark energy that make up the cosmos. Yet the CMB is not entirely straightforward. While it has answered many questions, it has also opened new ones. For instance, the exact nature of dark energy, which is believed to be responsible for the accelerated expansion of the universe, remains a puzzle. Additionally, the uniformity of the CMB challenges our understanding of the universe's origins and raises inquiries about its larger structure and fate. Each discovery related to the cosmic microwave background beckons further exploration, reminding us that our universe still holds many secrets waiting to be revealed. Black holes capture the imagination of scientists and enthusiasts alike due to their enigmatic nature and extreme characteristics. Created when massive stars exhaust their nuclear fuel, they collapse under their own gravity, resulting in a point of infinitely dense matter known as a singularity. Surrounding this singularity is the event horizon, a boundary beyond which nothing can escape the gravitational pull, not even light. This lack of visibility is what makes black holes so mysterious. We can only infer their existence through their effects on surrounding matter. The environment around black holes is also fascinating. In the process of material falling towards them, tremendous amounts of energy are released, often forming luminous accretion disks. These disks are composed of gas and dust spiraling into the black hole, heating up and emitting X-rays as they accelerate. Such emissions can provide clues about the black hole itself, revealing details about its mass and spin. Yet the black hole itself remains hidden from direct observation. This dance of light and gravity showcases the black hole's powerful influence while maintaining its elusive nature. Furthermore, black holes challenge our understanding of the laws of physics. The equations of general relativity, developed by Albert Einstein, describe the massive warping of space-time around these objects. Yet they also encounter limitations at the singularity, where our current understanding breaks down. The quest to unify general relativity with quantum mechanics, the rules that govern the atomic and subatomic realms, is a significant scientific endeavor, and black holes sit at the crossroads of these two domains, making them crucial to our understanding of the universe. Finally, the mysteries of black holes extend beyond their formation and characteristics. Questions still remain about their role in galaxy formation and evolution. This includes theories that suggest supermassive black holes, found at the centers of most galaxies, may influence star formation and the overall structure of galaxies. As we continue to probe the cosmos, black holes remain a profound puzzle, urging us to explore the very fabric of reality itself. Hawking radiation presents a fascinating twist to our understanding of black holes, a topic that has long intrigued scientists and enthusiasts alike. Traditionally, black holes were thought to be regions in space where gravity is so strong that nothing can escape, not even light. This powerful characteristic led many to believe that once something crosses the event horizon, it is lost to the universe forever. However, physicist Stephen Hawking introduced a groundbreaking concept that radically shifts this perspective. Hawking radiation suggests that black holes are not entirely black, but can actually emit radiation due to quantum mechanical effects near the event horizon. This radiation emerges from the interaction of particle-antiparticle pairs that constantly pop in and out of existence in empty space. When one of these particles falls into the black hole while the other escapes, it effectively leads to a slow draining of the black hole's mass. Over time, this process implies that black holes could eventually evaporate completely, a notion that stands in stark contrast to the conventional view of them as eternal cosmic prisons. This revelation has profound implications for our understanding of information. According to classical physics, information that falls into a black hole is irrevocably lost, leading to a paradox at the intersection of quantum mechanics and general relativity. Hawking's idea of radiation suggests the possibility that information could be carried away by escaping radiation, challenging the notion that everything consumed by a black hole disappears forever. This opens up deep philosophical and scientific questions about the fundamental nature of reality and information conservation in the universe. Ultimately, Hawking radiation not only reshapes our perception of black holes, but also prompts us to reconsider many foundational ideas in physics. It invites ongoing debate and research around the life cycle of black holes, their eventual fate, and the nature of space and time. As scientists continue to study this phenomenon, our understanding of the universe may evolve even further, continuously revealing the intricate dance between the immense gravity of black holes and the elusive principles of quantum mechanics. In recent years, the imaging of black holes has led to groundbreaking discoveries that significantly enhance our understanding of these enigmatic cosmic phenomena. One of the most notable breakthroughs came in April 2019, when the Event Horizon Telescope collaboration unveiled the first-ever image of a black hole's silhouette. This particular black hole, located in the center of the galaxy M87, presented a ring-like shadow surrounded by a glowing halo of hot gas, providing a striking visual confirmation of the existence of black holes and their distinctive traits. These imaging efforts have not only confirmed theories around black holes, but have also offered new insights into the nature of gravity itself. The image aligned well with the predictions made by Albert Einstein's general theory of relativity. When physicists analyzed the data, it showed the black hole behaving precisely as the theory suggested, thus reinforcing our trust in Einstein's framework. However, the more we investigate these mysterious objects, the more we uncover nuances that push the boundaries of our understanding and challenge existing models. The implications of these discoveries extend beyond merely confirming theories. For instance, studying the dynamics of the hot gas swirling around black holes helps scientists better comprehend how gravity influences matter, energy, and even light. These findings show that gravity is not just a force, but also plays a critical role in shaping the structure, dynamics, and evolution of galaxies themselves. This knowledge could eventually lead to answers regarding the universe's expansion and the elusive nature of dark matter. Moreover, these imaging advancements have sparked interests in combining observations with theoretical physics to explore what lies beyond current theories. As researchers refine their techniques using both radio and optical wavelengths, the potential for new discoveries grows. Each new image offers a glimpse into the unseen, helping humanity unravel the mysteries of black holes, challenging our understanding of the universe, gravity, and even the fundamental laws of nature as we know them. Mergers of black holes are some of the most extraordinary events in the universe, reshaping not just the black holes involved, but also the very fabric of space-time around them. When two black holes spiral towards each other, they create waves in space-time, known as gravitational waves. This phenomenon is a prediction of Albert Einstein's theory of general relativity, which describes gravity not as a force, but as a curvature of space-time caused by massive objects. As the black holes approach one another, they emit energy in the form of these waves, which travel at the speed of light, radiating outward and causing ripples in the fabric of space-time. Imagine tossing a stone into a still pond. The circles expanding from the point where the stone hits represent how gravitational waves propagate through the universe. When these waves reach Earth, they cause minute changes in distances that can be detected by incredibly sensitive instruments. The detection of gravitational waves was first achieved in 2015 by the LIGO Observatory. This groundbreaking observation marked a new era in astrophysics, allowing scientists to hear the universe in a way previously thought impossible. Each detection provides a wealth of information about the black holes involved, such as their masses and the energy released during the merger, often equivalent to several solar masses being converted into energy from the depths of space. Not only do these mergers reveal the existence of black holes in pairs, but they also deepen our understanding of their formation and growth in the cosmos. Each event is a chance to observe the extreme conditions of the universe, exploring the fundamental forces at play. Through gravitational wave observations, we are uncovering a new chapter in cosmic history, allowing us to witness the dance of black holes as they collide and transform the space around them. The idea of primordial black holes opens a fascinating window into the early universe and its formation. Unlike the black holes we often think about, which form from the gravitational collapse of stars, primordial black holes are believed to have formed shortly after the Big Bang. These early cosmic structures could have emerged from the density fluctuations and variations in temperature that existed in the primordial universe, leading to regions where gravity became strong enough to create black holes in the very first moments of cosmic history. The presence of primordial black holes could hint at a wealth of information regarding the conditions of the early universe. For instance, their existence might suggest that the universe went through times of rapid expansion and contraction, which aligns with theories like cosmic inflation. If primordial black holes formed from these fluctuations, they could provide evidence supporting ideas about how different regions of the early universe behaved and interacted, helping us understand the fundamental processes that set the stage for the universe as we know it today. Moreover, primordial black holes could also shed light on dark matter. Scientists believe that dark matter makes up a significant portion of the universe, yet it does not emit light and cannot be directly observed. If primordial black holes existed in sufficient numbers, they could constitute a portion of dark matter. This suggests that not only could we learn more about the early configurations of the universe, but we might also gain insights into the elusive dark matter that continues to puzzle astronomers. The study of primordial black holes serves as a bridge connecting the birth of the universe to our current cosmic landscape. By investigating their properties and potential impact, scientists push forward our understanding of fundamental questions about the universe's origin, evolution, and the material that shapes it. This ongoing inquiry continues to ignite curiosity, opening doors to a deeper understanding of our cosmic surroundings. The theories of relativity, proposed by Albert Einstein in the early 20th century, fundamentally altered how we understand the relationship between time and space. Before relativity, time was viewed as a constant, flowing uniformly for everyone, everywhere. This view made it easy to separate time from the three dimensions of space. However, Einstein's insights revealed that time and space are interconnected in a profound and dynamic way, creating what we now call space-time. At the heart of Einstein's special theory of relativity, introduced in 1905, is the idea that the laws of physics are the same for all observers, regardless of their relative motion. This theory shows that as an object moves closer to the speed of light, time begins to slow down for that object compared to a stationary observer. This phenomenon, known as time dilation, indicates that time is not an absolute measure but is relative, depending on the observer's speed and position in the universe. Einstein further expanded this concept in his general theory of relativity, released in 1915. This theory describes gravity not as a simple force, but as a curvature of space-time caused by mass. When a massive object, like a planet or a star, warps the fabric of space-time, it affects how time flows. For example, Clocks situated closer to a massive object run slower compared to those further away. This means that time passes at different rates depending on where you are in relation to massive bodies, a concept that has profound implications for how we perceive the passage of time across the cosmos. Together, these theories challenge our intuitive notions of time, encouraging us to see it not as a constant backdrop, but as a flexible, interconnected part of the universe. They invite us to imagine a universe where time can stretch, shrink, and bend, creating a landscape where our everyday experiences of time are just one small facet of a much larger, complex reality. Each interaction between time and space deepens the mystery of the cosmos, inviting further exploration and understanding of our place within it. Time dilation is a fascinating concept rooted in the theories of relativity, which reveal the intricate relationship between motion, gravity, and the passage of time. At the heart of this idea is the understanding that time does not flow at a constant rate for all observers. Instead, it is influenced by factors such as speed and gravitational fields. According to Albert Einstein's theories, as an object moves faster or is subjected to a stronger gravitational pull, time will pass more slowly for it when compared to a stationary observer in a weaker gravitational field. Imagine an astronaut traveling through space at a substantial fraction of the speed of light. For the astronaut, time feels normal, and days may pass as usual. However, for people back on Earth, significantly more time might have elapsed. This phenomenon showcases how extreme velocities can stretch time, resulting in what we call time dilation. The faster an object travels, the more pronounced this effect becomes, prompting some scientists to view time as elastic, bending and stretching in response to speed. Gravity plays a crucial role as well. Massive bodies like planets or black holes generate strong gravitational fields that warp the fabric of space-time. This warping causes clocks positioned closer to such massive objects to tick more slowly compared to clocks placed further away. For instance, time moves a bit more quickly for someone standing on a tall mountain than for someone at sea level, due to the difference in gravitational force. This connection between gravity and time highlights that our experience of time is not universal. Rather, it's deeply intertwined with how fast we are moving and how close we are to massive objects. Together, these insights reveal a profound truth. Time is not merely a constant ticking away at the same rate, but a dynamic force influenced by motion and gravity. They challenge our intuitive understanding and remind us that the universe operates in ways that can exceed our wildest imaginations. The beauty of science lies in uncovering these complexities, illuminating how interconnected our reality truly is. Wormholes, often described as tunnels connecting different points in space and time, intrigue both scientists and science enthusiasts alike. In modern theoretical physics, these fascinating structures arise from the equations of general relativity, which describe how gravity affects the fabric of space-time. Picture space-time like a two-dimensional sheet of rubber. If you were to create a tunnel through that sheet, you could effectively shorten the distance between 2 points. This tunnel is what we call a wormhole. There are several types of wormholes proposed by scientists, but the most famous is the Einstein-Rosen bridge. This type of wormhole connects distant regions of our universe, or even different universes, potentially allowing for instantaneous travel across vast cosmic distances. However, the concept is laden with complexities. For instance, many theoretical wormholes are unstable and would collapse before anything could pass through them. To remain open, they would require a form of exotic matter with negative energy density, a substance that has not been observed in the universe as we know it. The implications of wormholes stretch far beyond mere travel. If stable wormholes exist, they could revolutionize our understanding of the universe, presenting opportunities for communication across vast distances, or even enabling time travel, at least in theory. Although such ideas sound like science fiction, they prompt deep philosophical questions about the nature of reality, causality, and our place in the cosmos. Imagine having the ability to explore not only different locations in space, but also different moments in time. Despite the tantalizing prospects of wormholes, they remain firmly in the realm of theoretical physics for now. Ongoing research in quantum gravity and related fields might one day yield discoveries that bring us closer to understanding these enigmatic structures. Until then, wormholes continue to spark the imagination, reminding us of the mysteries that still lie beyond our understanding of the universe. The concept of time travel intrigues our imagination and raises fascinating questions, particularly around paradoxes that challenge our understanding of causality. One of the most famous paradoxes is the grandfather paradox. Imagine traveling back in time and inadvertently preventing your grandfather from meeting your grandmother. If that were to happen, you would never be born. If you were never born, how could you have traveled back in time in the first place? This paradox forces us to confront the complexities of cause and effect, as our intuitive understanding of time is turned on its head. Another notable paradox is the bootstrap paradox. This occurs when an object or piece of information is sent back in time, creating a scenario where its existence has no clear point of origin. Picture a scenario where a time traveler brings back a famous work of art to the past, where it then inspires its original creation. In this case, the art appears to exist without anyone ever having created it, leaving us pondering the very nature of creation and existence. Such challenges to causality blur the lines of what it means for events to be connected in a linear fashion. These paradoxes also involve implications for our understanding of time itself. If time is a linear sequence of events, as most of us perceive it, then any disruption could lead to inconsistencies in our universe. The experience of time travel, as depicted in various forms of media, suggests alternate timelines or parallel universes. Some theorists propose that traveling back in time might create a branch in the timeline rather than altering the original events. This idea enriches the discussion, opening doors to a multitude of realities where history could unfold differently. Ultimately, these paradoxes invite us to rethink not just time travel, but the very structure of reality and time itself. They challenge our perceptions, urging us to explore the fascinating interplay between time, causality, and existence. In grappling with these questions, we expand our understanding of the universe and our place within it, recognizing the intricate tapestry of events that define our shared reality. Cosmic strings are fascinating hypothetical objects that arise in certain cosmological theories. They are essentially one-dimensional defects that could have formed in the early universe when it cooled and underwent phase transitions. Imagine them as incredibly thin, infinitely long strands of energy that weave through the fabric of space-time, a bit like yarn in a grand tapestry. These strings may be composed of various forms of energy and could help us understand the fundamental structure of the universe. The existence of cosmic strings could provide valuable insights into the nature of gravity and how it interacts with space-time. These strings would create a gravitational field that could affect the surrounding space. This means that if cosmic strings exist, they might bend light in unusual ways, leading to unique observational effects. Astronomers are always on the lookout for evidence of these disturbances, which could potentially confirm the existence of cosmic strings. Moreover, cosmic strings may have enormous implications for our understanding of the universe's early moments. They might be linked to concepts like inflation, a rapid expansion that theorists propose occurred shortly after the Big Bang. If cosmic strings were present, they could influence the distribution of matter and energy in the universe, which would help explain why galaxies and large-scale structures are distributed the way they are today. Cosmic strings serve as an intriguing bridge to explore profound questions about our universe. While they remain theoretical, their potential existence could reshape our understanding of the fabric of space-time and the fundamental forces at play. They serve as a reminder of just how much we still have to learn about the cosmos and the hidden complexities that lie beyond our current understanding. String theory is a fascinating and intricate framework in theoretical physics that seeks to explain the fundamental nature of our universe at its most basic level. At its core, string theory posits that the building blocks of the universe are not point-like particles as traditionally thought, but rather tiny vibrating strings of energy. These strings can oscillate in different ways, and it is this vibration that determines the properties of particles, such as their mass and charge. Envisioning particles as strings allows physicists to explore a deeper, more unified understanding of matter and forces. One of the remarkable aims of string theory is to unify the four fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces. In classical physics, these forces seem unrelated and are described by different theories. However, string theory proposes that all of these forces and the particles associated with them emerge from different modes of vibration of these strings. This unifying perspective hints at the possibility that there is a single underlying principle that governs all physical phenomena. The complexity of our universe challenges current scientific theories, especially in reconciling quantum mechanics and general relativity. String theory attempts to bridge this divide by offering a framework where both gravitational and quantum forces can coexist. For instance, when studying black holes or the very early universe, string theory provides tools to understand the interactions of these extremes, potentially leading to insights that classical theories alone cannot offer. Despite its elegance and appeal, string theory remains a work in progress. It has not yet been confirmed through experiments, partly due to the incredibly small size of the strings, which are thought to vibrate at scales much tinier than we can currently measure. Nevertheless, string theory continues to inspire and challenge scientists as they search for a deeper understanding of the universe, tantalizing us with the prospect of a grand unification of all forces and a more complete understanding of reality. The multiverse theory presents an extraordinary and complex expansion of our understanding of reality. At its core, this theory suggests that our universe is not the only one, but rather a vast collection of universes, each potentially governed by different laws of physics and constants. Imagine a massive cosmic tapestry, where each thread represents a different universe. Some may be similar to ours, while others could be radically different, with distinct properties or forms of life. This theory arises from several branches of science, including quantum mechanics and cosmology. In quantum mechanics, for instance, there's a concept called superposition, where particles can exist in multiple states simultaneously. Some interpretations of this notion suggest that every possible outcome of a quantum event might create a separate universe, leading to an almost endless array of realities branching off from each decision we encounter. This idea reshapes our understanding of chance and destiny, implying that every choice we make creates divergent paths of existence. In the realm of cosmology, the concept of cosmic inflation, the rapid expansion of the universe just after the Big Bang, adds another layer to the multiverse theory. This rapid growth could lead to bubbles forming in space-time, with each bubble representing a separate universe, complete with varying characteristics. Within this context, our universe becomes merely one bubble in a larger cosmic foam, inviting us to reconsider what we previously understood as the totality of existence. Ultimately, the multiverse theory elevates philosophical questions about reality, existence, and even the concept of life itself. If countless universes exist, where the laws of nature may differ wildly, it opens avenues for discussions about the nature of consciousness, free will, and the significance of our choices. As we explore these mind-bending ideas, our understanding of reality transforms, encouraging us to ponder the universe's depth and the myriad of possibilities it holds beyond our own horizon. The nature of consciousness is one of the most profound and intriguing mysteries in both science and philosophy. Despite significant advancements in fields like neuroscience and psychology, many fundamental questions remain unanswered. For instance, we still do not fully understand how subjective experiences arise from the physical processes in the brain. This phenomenon, often referred to as the hard problem of consciousness, raises questions about the connection between our inner experiences and the physical universe. Another captivating question lies in whether consciousness is a unique characteristic of living organisms or if it exists in some form across the universe. As we explore the cosmos, the possibility of alien intelligence challenges our understanding of consciousness. Are there other beings out there with awareness, and if so, how does their perception of reality differ from ours? This exploration taps into deeper philosophical inquiries about the very nature of existence and awareness itself. Moreover, there's an ongoing debate about whether consciousness plays an active role in the universe or if it is merely a byproduct of complex biological processes. Some theories suggest that consciousness might influence reality and that our perceptions could help shape the universe. This notion introduces a fascinating interplay between consciousness and quantum mechanics, suggesting that our awareness could impact the behavior of subatomic particles. Ultimately, the quest to unravel the mysteries of consciousness is not just about understanding ourselves, but also about our place in the universe. As we ponder the nature of awareness, we might uncover insights that bridge science and spirituality, uniting our understanding of consciousness with the vastness of the cosmos. Each discovered layer of consciousness beckons further inquiry, igniting curiosity and wonder in the ongoing pursuit of knowledge. Quantum entanglement is a fascinating phenomenon that reveals the profound relationships between particles, no matter how far apart they may be. When two particles become entangled, their states become linked, meaning the condition of one particle instantaneously affects the other, regardless of the distance separating them. Imagine two dancers connected by an invisible thread. Even if one dances in New York and the other in Tokyo, any movement made by one is felt by the other. This interconnectedness stretches across the cosmos, illustrating a fundamental aspect of the fabric of the universe. What makes quantum entanglement particularly intriguing is its defiance of classical physics. Traditionally, we understood that information and influence could not travel faster than the speed of light. Yet experiments have shown that when entangled particles are measured, changes occur at a remarkable speed that seems to transcend this cosmic speed limit. This has led to debates and discussions about the nature of reality and the very essence of causality. Are these particles somehow communicating in a way we do not yet understand, or is our perception of distance itself fundamentally flawed? This concept challenges our intuitive notions of separation and locality. In our everyday experiences, things are usually connected by physical proximity and time. However, quantum entanglement suggests a universe where the traditional boundaries that separate entities blur. It proposes a picture where everything might be more interconnected than we can observe, revealing a deeper underlying unity in the cosmos. As scientists continue to explore this intriguing aspect of quantum mechanics, the implications go far beyond mere curiosity. They hint at revolutionary technologies such as quantum computing and secure communications, but they also provoke deep philosophical inquiries. What does it mean for our understanding of reality if entangled particles can influence each other across vast distances? This quest to understand intertwines with our age-old questions about the nature of the universe and our place within it, captivating our imaginations and expanding our grasp of physical laws. Speculative theories about alternative dimensions invite us to rethink the very fabric of our universe. Traditionally, physics has operated on a foundation of three spatial dimensions plus time, forming what we know as spacetime. However, concepts such as string theory propose the existence of additional dimensions beyond the familiar four. These extra dimensions, although not directly observable, could significantly alter how we understand gravity, forces, and particles at a fundamental level. In this perspective, the physical laws we adhere to, like gravity or electromagnetism, may behave differently when accounting for these unseen dimensions. For instance, string theory suggests that the fundamental particles we perceive are actually tiny vibrating strings existing in multidimensional space. The properties of a particle, such as its mass or charge, stem from how these strings vibrate in these additional dimensions. This proposition introduces a complex, richer structure of reality that challenges our long-held notions of how particles interact. Furthermore, the idea of parallel universes emerges from some theories regarding alternative dimensions. If multiple dimensions exist, it raises the possibility that there could be other versions of our universe, each with its own set of physical laws. In this framework, what we perceive as constants, like the speed of light, could vary in different dimensions, opening the door to entirely new forms of physical phenomena and laws that defy traditional logic and experience. Ultimately, These speculative theories not only broaden our understanding of physics, but also spark an invigorating discussion about the nature of reality. They encourage scientists and enthusiasts alike to explore the cosmic landscape of possibilities that lie beyond our perceptual grasp, reminding us how much we have yet to uncover about the universe we inhabit. Cosmic archaeology is a fascinating field that focuses on understanding the history of the universe by examining its structure and composition. One primary method used in this discipline is observing the light from distant galaxies. As light travels across vast distances, it carries information about the objects it has encountered along the way. By studying the spectrum of this light, scientists can determine the chemical composition of these galaxies, their distances, and even their velocities. This information helps reconstruct how galaxies formed and evolved over billions of years. Another intriguing approach in cosmic archaeology is the study of cosmic microwave background radiation. This faint glow fills the universe and is a remnant from the early stages of the Big Bang. Researchers analyze fluctuations in this radiation to gain insights into the conditions of the universe just after its formation. These fluctuations inform us about the density and distribution of matter, shedding light on how structures like galaxies and galaxy clusters emerged over time. To delve even deeper, scientists utilize advanced simulations and computational models. These models incorporate known physics and data from various observations to mimic the evolution of the universe. By comparing simulated results with real-world observations, researchers can validate theories of cosmic evolution and refine their understanding of how galaxies interacted, merged, and transformed over cosmic time. Lastly, the study of ancient stars plays a crucial role in cosmic archaeology. Some stars in our galaxy are extremely old, dating back to the early universe. Analyzing their chemical compositions not only reveals insights about the conditions in which they formed, but also preserves the story of the elements created in the cosmos. These ancient celestial bodies serve as time capsules, allowing us to piece together the timeline of stellar evolution and the processes that shape the universe as we know it today. Globular clusters are fascinating relics of the early universe, providing key insights into the process of galaxy formation. These dense collections of stars, often containing hundreds of thousands to millions of stars, are typically found orbiting the outskirts of galaxies. Their ancient nature means many of these clusters formed around the same time as the earliest galaxies, serving as a cosmic time capsule, offering astronomers a glimpse into conditions several billion years ago. One of the primary reasons globular clusters are vital to our understanding of galaxy formation is their age. Many of these clusters are among the oldest objects we can observe, with some estimated to be over 13 billion years old. By studying the properties of their stars, such as their composition and luminosity, scientists can infer what the conditions were like in the early universe. This, in turn, sheds light on processes like star formation and chemical enrichment that occurred in the nascent galaxies where these clusters arose. Moreover, globular clusters help astronomers learn about the environments in which galaxies formed. They tend to be rich in certain elements and elements that are remnants of the first stars, which exploded in supernova. These early explosive events seeded the neighboring gas and dust with heavier elements that became the building blocks for future generation stars and the galaxies that host them. Thus, analyzing the composition of globular clusters can indicate the extent of star formation and chemical evolution in their surrounding environments. By studying globular clusters, astronomers piece together the puzzle of how galaxies formed and evolved over time. They offer unique insights into the cosmic conditions of the early universe and highlight the intricate dance of formation that has shaped our night sky. As we continue to explore these ancient stellar groups, we deepen our understanding of not just our own galaxy, but also the universe as a whole. Studying meteorites offers us a fascinating window into the early solar system and the materials that formed it. When we examine these space rocks, we are essentially looking at remnants from the time before Earth was fully formed. Many meteorites are fragments that originated from asteroids or are even pieces of planets that no longer exist. By analyzing their composition, scientists can glean valuable information about the conditions and processes that were present over 4 billion years ago, when our solar system was still a swirling disk of gas and dust. One of the key insights meteorites provide is the mixture of elements that formed the building blocks of our planets. For instance, certain types of meteorites, known as chondrites, contain tiny spherical particles that are thought to be among the oldest materials formed in the solar system. These particles, called chondrules, can tell us about the temperatures and environments in which they formed. By studying their isotopic ratios, essentially the variations of elements like oxygen and carbon, scientists can reconstruct the conditions on the early solar system and the processes that led to planetary formation. Moreover, meteorites can reveal the chemical complexity that existed at that time. Some contain organic compounds, the foundational molecules for life as we know it. The presence of such compounds suggests that the building blocks of life may have been widespread throughout the early solar system, perhaps even hinting that the ingredients for life did not originate solely on Earth, but were delivered here by meteorites. This tantalizing possibility pushes the boundaries of our understanding and leads to further questions about life beyond our planet. Finally, beyond mere chemistry, meteorites also tell stories of impacts and collisions. They serve as records of the violent history that characterized early solar system dynamics. By studying the physical structures and impact marks on meteorites, scientists can learn about the frequencies and scales of collisions, which ultimately shaped the planets we know today. Meteorites are like time capsules, filled with the less explored stories of our cosmic origins and the intricate dance of elements that paved the way for the worlds we inhabit now. Ancient light and cosmic rays serve as remarkable time capsules, providing unique insights into the early universe. When we talk about ancient light, we're often referring to the glow left over from the Big Bang, called cosmic microwave background radiation. This radiation filled the universe about 380,000 years after the Big Bang, when protons and electrons combined to form hydrogen atoms. Before this point, the universe was a hot, dense fog of particles, making it opaque. As the universe expanded and cooled, it became transparent, allowing this light to travel freely through space, reaching us billions of years later. This cosmic microwave background radiation is a snapshot of the universe at a very early stage, and scientists have studied its variations to learn about the conditions that prevailed back then. These variations, or fluctuations, in temperature related to density differences, represent the seeds of all structures we see today, like galaxies and stars. By analyzing this ancient light, cosmologists can glean information about the universe's composition, its expansion rate, and even the nature of dark matter and dark energy. It's like peering through a window into the past, revealing a wealth of information about how the cosmos evolved. On the other hand, cosmic rays, which are high-energy particles mostly originating from outside our solar system, also provide valuable clues about the universe's conditions. These cosmic rays travel at nearly the speed of light and are a mix of protons, helium nuclei, and heavier atomic nuclei. When they collide with the atmosphere or objects in space, they can produce a cascade of secondary particles, which researchers study to understand the processes that generated them. By understanding the origins and power of cosmic rays, scientists can gather information about extreme events in the universe, like supernova explosions or the activity of black holes. Cosmic rays act as messengers that carry information from the most energetic environments, helping bridge our understanding of the early universe with more recent astronomical phenomena. Together, ancient light and cosmic rays not only enrich our knowledge of the cosmos, but also ignite a sense of wonder about the universe's journey through time. The oldest stars in the universe are often referred to as population 2 stars. These ancient celestial bodies formed shortly after the Big Bang, around 13 billion years ago, and serve as time capsules, offering profound insights into the early universe. By studying these stars, astronomers can piece together the conditions that prevailed in the cosmos long before our solar system took shape. One of the most significant discoveries is that many of these oldest stars are incredibly metal poor. meaning they contain very few elements heavier than hydrogen and helium. This is expected, as the first generations of stars primarily produced these light elements through nuclear fusion. When they eventually exploded as supernovae, they enriched the surrounding gas with heavier elements like carbon, oxygen, and iron. By analyzing the elemental compositions of these ancient stars, we can understand how the universe transitioned from a primordial state dominated by simple elements to one rich in complexity. Another fascinating aspect of studying these stars involves their formation and the role of structure in the universe's evolution. Older stars tend to reside in the halo of our Milky Way galaxy, as well as in globular clusters. Their presence suggests a history of galactic formation where smaller stars merged or interacted, forming larger structures. By observing how these stars behave and their distribution across the cosmos, scientists gain clues about the process of galaxy formation and the influence of dark matter in shaping the universe. Moreover, these ancient stars help us trace the history of cosmic events, such as supernova explosions and the formation of galaxies. By examining the oldest stars, we can also explore theories about the early universe, including the reionization period, when light from the first stars, galaxies, and black holes transformed the universe from an opaque state to one filled with light. Each new discovery regarding these ancient stars enhances our understanding of cosmic evolution, revealing the intricate and often surprising path that led to the universe as we know it today. Scientists investigate the nature of gravity through a combination of theoretical concepts and experimental techniques that unravel its mysteries and its pivotal role within the universe. At the core of this investigation is the understanding of gravity as a fundamental force that governs the motion of celestial bodies, from the smallest particles to the largest galaxies. One of the primary frameworks we use to explore gravity is Albert Einstein's theory of general relativity, which describes gravity not as a force in the traditional sense, but as a curvature of space and time caused by mass. To test these theories, scientists employ a variety of innovative methods. Observations of planetary motions, star orbits, and the trajectories of comets all provide essential data. An important recent advancement came from gravitational wave astronomy, a field that emerged following the groundbreaking detection of gravitational waves in 2015. These ripples in the fabric of space-time, caused by massive cosmic events like the collision of black holes, not only confirm Einstein's predictions, but also open a new window into understanding gravitational dynamics on a cosmic scale. In addition to observational techniques, scientists conduct experiments in controlled environments to explore gravity's nuances. For example, researchers use drop towers and laser interferometry to measure how objects behave under gravitational influence. They analyze how gravity affects time, as demonstrated by the minute variations in clocks at different altitudes, a phenomenon known as gravitational time dilation. Ultimately, the quest to unravel gravity's elusive nature is a blend of observation, experimentation, and theory. Each new discovery not only reinforces our understanding of gravity, but also raises further questions about its role in the grand tapestry of the universe. The journey continues, as scientists look to deepen their comprehension of gravity's complexities and its essential contribution to the cosmos. Modified gravity theories challenge the traditional understanding of gravity as proposed by Isaac Newton and later refined by Albert Einstein. These theories suggest that gravity itself may behave differently under certain conditions, especially in the vast emptiness of space where dark matter and dark energy are prevalent. This has significant implications for our understanding of these mysterious components of the universe. One of the main implications is that modified gravity could potentially eliminate the need for dark matter altogether. Some models propose that the gravitational effects attributed to dark matter might actually stem from alterations in the gravitational force at large scales. This challenges the prevailing notion that there are unseen masses exerting a gravitational pull on galaxies, as modified gravity may explain the rotations of galaxies and the movement of galaxy clusters through adjustments to the laws of gravity itself. When it comes to dark energy, which drives the accelerated expansion of the universe, modified gravity theories also offer fresh perspectives. Instead of introducing a mysterious force or energy that fills all of space, these theories suggest that the acceleration could result from the changing dynamics of gravity over cosmic distances. This implies that our universe's fate could be influenced more by the characteristics of gravity than by an unknown energy field. Ultimately, exploring modified gravity theories invites us to reconsider our entire framework for understanding the cosmos. Each new insight not only deepens our appreciation of the universe's complexity, but also nudges us toward a more unified theory of physics that might weave together gravity, dark matter, and dark energy into a coherent narrative. As researchers continue to explore these theories, they may lead us to breakthroughs that fundamentally alter our understanding of the universe and our place within it. Gravity is the invisible force that dances between celestial bodies, shaping the cosmos in ways that are both profound and intricate. In the beginning, when a cloud of gas and dust floats through space, gravity begins to exert its influence. This cloud, often called a molecular cloud, starts to collapse under its own weight. As it contracts, the material at its center gathers energy and heats up, eventually forming a new star surrounded by a rotating disk of leftover material, the birthplace of potential planets. Within this rotating disk, gravity takes center stage. Smaller clumps of debris collide and coalesce, gradually building up larger bodies. Over time, some of these clumps become planets, while others can take on the form of moons, asteroids, or comets. The gravitational tug-of-war among these forming bodies is critical. It not only determines their orbits, but can also lead to significant events, like collisions, which play a role in shaping the characteristics of planets. For instance, the impact that is theorized to have created Earth's moon would have been possible only through gravitational interactions. As planetary systems evolve, gravity continues to hold sway over their development. Planets orbit their stars in stable paths, governed by the gravitational pull between them. Over millions of years, this intricate ballet can change significantly. Planets may migrate inward or outward, influenced by interactions with other planets or the redistribution of gas in the protoplanetary disk. Additionally, the balance between a star's gravity and the centrifugal force from the planet's orbits determines the characteristics and stability of the entire system. The influence of gravity extends beyond mere formation and orbits. It plays a crucial role in the potential for life. The mass of a planet affects its ability to retain an atmosphere, which is significant for supporting life. The delicate balance that gravity creates ensures that conditions on planets can be just right for life to thrive, or conversely, to be hostile. Thus, gravity not only orchestrates the formation and evolution of planetary systems, but also shapes possibilities for life in the universe, highlighting the profound interconnectedness of cosmic forces. Gravity waves, or gravitational waves, present intriguing mysteries in the field of astrophysics. These ripples in space-time are caused by some of the most energetic and cataclysmic events in the universe, such as colliding black holes or neutron stars. The first detection of gravitational waves in 2015 marked a monumental milestone, confirming a prediction made by Albert Einstein over a century earlier. Yet the journey to fully understanding these waves is packed with questions about their origins and effects. One major mystery involves the strength and frequency of these waves. These signals travel vast distances across the cosmos, yet they carry only slight disturbances. This raises questions about how we can detect them, as well as what we can learn from their variations. For example, when two massive objects orbit each other, they create waves that provide us with data not just about their masses, but also their distances and even their spins. The more we learn, the more we realize how these subtle waves can disclose the structure and behavior of the universe itself. Moreover, gravitational waves open up new avenues for understanding cosmic events. They signal processes that are invisible to traditional telescopes. While we might gaze at the night sky and see light from distant stars, gravitational waves allow us to observe phenomena obscured by dust and gas. This is particularly important when studying the aftermath of supernova explosions or the merger of compact stellar objects, offering insights that could deepen our knowledge of elements like neutron-star collisions and their role in heavy element formation. Lastly, the events that produce gravitational waves often signal the birth of new observables in the universe. With the ongoing upgrades and future projects in gravitational wave astronomy, we stand at the threshold of a new era in understanding our cosmos. These waves may help unravel the mysteries behind dark matter and dark energy, revealing not only how the universe was born, but also how it continues to evolve. Each detection propels us closer to unlocking these cosmic secrets, reminding us of the vast and enigmatic nature of the universe we inhabit. At the heart of modern physics lies a fundamental tension between two great theories: general relativity and quantum mechanics. General relativity, formulated by Albert Einstein, beautifully explains the gravitational interactions of massive objects and the curvature of space-time. On the other hand, quantum mechanics reveals the peculiar behaviors of particles at the smallest scales, governing the subatomic realm. The challenge arises because these theories operate under very different principles. While general relativity is a smooth, continuous theory, quantum mechanics thrives in a world of probabilities and uncertainties. To bridge this gap, physicists have proposed the concept of quantum gravity, which seeks a unified framework that incorporates both gravitation and quantum effects. One intriguing idea involves treating gravity not as a force, but as a property of space-time itself, composed of quantized gravitons, which would be the particles responsible for carrying the gravitational force. This perspective aligns more closely with other fundamental forces, which are understood through their associated particles. Yet detecting these hypothetical gravitons remains a significant hurdle, one that scientists are still striving to overcome. Several approaches to quantum gravity have emerged, showcasing the creativity and depth of research in this field. Loop quantum gravity, for instance, posits that space-time has a discrete structure at the smallest scales, akin to a mesh of tiny loops. This theory suggests that even the fabric of the universe may be woven from quantized threads, leading to fascinating implications about the nature of reality itself. Conversely, string theory proposes that the basic building blocks of the universe are one-dimensional strings rather than point-like particles. In this scenario, gravity emerges from the ways these strings vibrate, effectively creating a tapestry that weaves together quantum mechanics and general relativity. Despite these progressive theories, scientists acknowledge that a complete understanding of quantum gravity may still be years, if not decades, away. Yet the pursuit itself is rich with discoveries that have the potential to revolutionize our understanding of the cosmos. As researchers continue to explore this intersection, they unveil not just the workings of gravity at the quantum level, but also the very nature of space and time, reminding us that in science, every question leads to new realms of wonder and inquiry. Human exploration of space has transformed dramatically since our first tentative steps beyond our planet. It all began in the 20th century when scientists built the groundbreaking technology necessary for such ambitious ventures. The launch of the first artificial satellite, Sputnik, by the Soviet Union in 1957 marked a crucial milestone. This not only ignited the space race but also shifted our perspective, making it clear that space exploration was possible and could yield astonishing discoveries. Following this, the United States responded with the Explorer 1 satellite, leading to a series of missions that included the Mercury and Gemini programs. These missions were fundamental in testing human endurance and developing the life support systems necessary for spaceflight. The monumental achievement of landing humans on the Moon in 1969 during the Apollo 11 mission brought the whole world together in awe. Astronauts Neil Armstrong and Buzz Aldrin walked on the lunar surface, fulfilling a dream that had captured the imagination of many for centuries. As we moved into the late 20th century and beyond, the focus shifted from simply reaching new frontiers to creating sustainable human habitats in space. The development of the International Space Station in the late 1990s represented a hallmark of international cooperation. Astronauts from various countries live and work together in this remarkable laboratory orbiting Earth, contributing to scientific advancements across disciplines. Research conducted aboard the ISS has provided crucial insights into everything, from material science to the effects of microgravity on the human body. Looking to the future, we are now on the brink of exciting developments in space exploration. Missions to Mars are becoming a priority, with both government space agencies and private companies planning journeys that aim to land humans on the Red Planet. Additionally, the exploration of outer planets and their moons, such as Europa and Enceladus, continues to offer tantalizing possibilities. Each discovery not only expands our scientific knowledge, but also deepens the human connection to the cosmos, inspiring future generations to look up at the stars and wonder what else lies beyond our world. Throughout history, celestial events have captivated cultures across the globe, serving as harbingers of change, symbols of power, and reflections of humanity's place in the universe. Ancient civilizations closely observed the movement of the stars, the phases of the moon, and the dance of planets, believing these celestial bodies held significant sway over earthly affairs. For instance, in many cultures, a total eclipse of the sun was interpreted as an omen, often signaling impending disaster or the wrath of deities. In Mesopotamia, the Babylonians meticulously recorded celestial phenomena, creating one of the earliest forms of astronomy. They linked planetary movements to agricultural cycles, using their knowledge of the night sky to predict seasonal changes, which were vital for farming societies. Similarly, in ancient Egypt, the heliacal rising of the star Sirius marked the beginning of the annual flooding of the Nile, an event crucial for their agricultural prosperity. These interpretations not only guided daily life, but also reinforced social structures, as priests and astronomers held significant authority by virtue of their knowledge. The Greeks expanded upon earlier astronomical insights, intertwining their study of the heavens with mythology and philosophy. Figures like Ptolemy structured a geocentric model of the universe, where Earth stood at the center, influencing not only scientific thought for centuries, but also the worldview of European cultures. During the Renaissance, a shift occurred with the heliocentric model proposed by Copernicus, sparking a revolution in science and a re-evaluation of humanity's role in the cosmos. As we moved into the modern era, celestial events continued to resonate deeply within societies. The 20th century saw a revival of interest in astrology, where many turned to the stars for guidance in their personal lives. Moreover, significant astronomical events, such as lunar landings and solar eclipses, have been celebrated as monumental achievements, invoking a sense of collective pride and curiosity. Today, as we analyze the cosmos with sophisticated technology, the relationship between celestial events and society remains vibrant, constantly inviting us to ponder our connection to the universe. Technology plays a pivotal role in our quest to understand the universe, acting as the bridge between human curiosity and cosmic knowledge. From telescopes that peer deep into space to particle accelerators that reveal the building blocks of matter, each technological advancement opens new doors to discovery. Consider the Hubble Space Telescope, which has provided breathtaking images of distant galaxies and helped us determine the rate of the universe's expansion. These images not only feed our imagination, but also give scientists concrete data to work with, enabling the formulation of theories about the universe's origins and structure. In addition to telescopes, advancements in computer technology have revolutionized our ability to process vast amounts of data. Observatories collect more information in a day than scientists could analyze in a lifetime. High-powered computers equipped with sophisticated algorithms sift through this data, identifying patterns that could lead to breakthroughs in our understanding of dark matter and dark energy. These invisible components make up nearly 95% of the universe, and technology is our key to unraveling their secrets. Moreover, technology has facilitated international collaboration like never before. Instruments such as gravitational wave detectors have enabled scientists from around the world to work together on projects that were once the domain of single nations. These collaborations allow for pooling of resources, expertise, and intellectual power, greatly enhancing our scientific output. The detection of gravitational waves, for instance, confirmed a major prediction of Einstein's general theory of relativity and opened a new field of astronomy. As we look to the future, emerging technologies promise to delve even deeper into cosmic mysteries. Innovations like quantum computing and next-generation space telescopes will likely unveil phenomena we have yet to even imagine. Each technological leap provides not just answers but also new questions, echoing the age-old truth that the pursuit of knowledge is a never-ending journey. In many ways, technology is the vessel that carries humanity through the vast seas of the universe, guiding us towards new horizons of understanding. Public engagement with astronomical discoveries plays a vital role in sparking interest among young minds and inspiring the next generation of scientists. When communities gather for events like star parties or planetarium shows, they are not just passive observers, they become active participants in a shared pursuit of knowledge. This direct interaction with astronomy ignites curiosity and wonder, guiding children and teenagers to explore the vastness of space and the mysteries it holds. One of the most compelling aspects of public engagement is its ability to make complex ideas accessible. Astronomers and educators often convey discoveries in a way that resonates with everyday experiences. For example, through storytelling that weaves in the latest findings about black holes or exoplanets, young audiences can connect scientifically rigorous concepts to the world around them, fostering a sense of relevance. This approach not only catches their attention, but also encourages them to think critically and ask questions, both fundamental skills in scientific inquiry. Encouraging personal exploration outside organized events is equally important. Telescope clubs, science fairs, and citizen science projects offer hands-on experiences where young people can contribute to real scientific research, such as tracking comet appearances or monitoring the behavior of distant galaxies. These activities create a sense of ownership and highlight that science is not just for experts in labs, it is a dynamic journey where everyone can contribute to our understanding of the universe. In a world increasingly dominated by technology, maintaining an awe for our cosmos is essential. The excitement generated through public engagement can lead to new avenues of exploration, guiding students toward careers in science, technology, engineering, and mathematics. By fostering a culture of inquiry and encouraging participation in astronomy, we create a framework where future scientists thrive, ensuring we have the bright minds needed to unlock the secrets of the universe in years to come. The search for extraterrestrial intelligence, often referred to as SETI, offers a profound reflection of human curiosity and our boundless imagination. Since the dawn of civilization, humans have looked to the stars, wondering if we are truly alone in the universe. This quest is not just about finding alien life, it's about seeking understanding of our place in the cosmos. Each radio signal sent into the void, each telescope aimed at distant stars, embodies a deep thirst for knowledge and an inherent desire to connect with something greater than ourselves. This endeavor illustrates how deeply our imagination is intertwined with our scientific pursuits. When we contemplate the possibility of other life forms, we aren't merely searching for facts, we are envisioning entire worlds. We picture civilizations with their own histories, cultures, and technologies, often inspired by science fiction. These imaginative journeys fuel innovative thinking and technological advancements. Every time we explore the potential for life beyond Earth, we push the boundaries of what we believe is possible, both in science and in our understanding of life itself. Moreover, the search for extraterrestrial intelligence challenges us to reflect on our own existence. In pondering what alien civilizations might resemble, we also consider what it means to be human. It invites us to examine our behaviors, our planetary stewardship, and our often conflicted relationship with technology. Are we nurturing enough to optimize our planet for life? How do we communicate and form connections? In many ways, the questions we seek to answer in our search for extraterrestrial intelligence mirror the larger questions we grapple with on Earth. Ultimately, the pursuit of extraterrestrial intelligence shines a light on our shared humanity. In an age of unprecedented scientific inquiry, our burning desire to know if we are alone in the universe reveals our hunger for connection and meaning. It illustrates that while we may be separated by vast distances in space, our curiosity knows no boundaries. Whether we ultimately find life among the stars or not, this quest drives us to explore, to dream, and most importantly, to understand ourselves better in the cosmic tapestry of existence. As we look to the next decade, the world of space exploration is about to open up with several exciting missions. Notably, NASA's Artemis program is poised to take center stage. With the goal of returning humans to the moon by 2025, Artemis aims to establish a sustainable presence on the lunar surface. This endeavor isn't just about setting foot on the moon again. It will pave the way for future explorations to Mars and beyond. Scientists hope to analyze the moon's resources and gather valuable data on its geology that could deepen our understanding of the early solar system. Another fascinating mission on the horizon is the James Webb Space Telescope, which is already underway in its quest to explore the universe's most intriguing secrets. Set to launch in December 2021, it will provide unprecedented insights into the formation of stars and galaxies, and even the potential for life beyond Earth. By capturing light from the first galaxies that formed, the telescope aims to answer fundamental questions about the origins of our cosmos, bridging gaps that previous telescopes could not. Meanwhile, the European Space Agency is launching the Jupiter Icy Moons Explorer, or JUICE, for a mission starting in 2023. This spacecraft will study Jupiter's largest moons, particularly Europa, Ganymede, and Callisto. Scientists suspect that beneath Europa's icy crust lies a vast ocean that could harbor conditions suitable for life. JUICE will focus on understanding the moon's potential habitability and their geological activity, diving deeper into the search for extraterrestrial life in our own solar system. These missions, among others, will undoubtedly enhance our knowledge of not only our planetary neighbors, but also the broader cosmic environment. As scientists unravel these mysteries, we can expect a wealth of discoveries that redefine our understanding of the universe and our place within it. Each upcoming mission is a step closer to answering age-old questions about existence, life, and the fundamental workings of space itself. Advancements in telescope technology are set to revolutionize our understanding of distant galaxies and cosmic objects, opening up new frontiers in astronomy. As telescopes improve, they become more sensitive and capable of detecting faint light from far-off places in the universe. The delicate balance of optics, sensors, and software means that astronomers can gather more information than ever before, allowing us to observe galaxies that formed billions of years ago. One exciting development is the shift to larger telescopes, both ground-based and space-based. Larger mirrors can collect more light, making it possible to see dim galaxies that were previously too faint to study. For instance, the James Webb Space Telescope features a mirror that is about 6.5 meters across. This immense size allows it to look further back into time and space, unveiling celestial phenomena from the early universe. By observing different wavelengths of light, such as infrared, telescopes can penetrate clouds of dust that often obscure our view of these ancient formations. Moreover, advancements in adaptive optics are enhancing ground-based telescopes' capability to produce clear images, even through the Earth's turbulent atmosphere. By using advanced computer systems, these telescopes can adjust in real time to distortions caused by atmospheric conditions. This breakthrough improves the resolution of the images they capture, offering a clearer view of distant galaxies, star clusters, and other intriguing objects beyond our solar system. As we gather more detailed data about the structure, composition, and behavior of these distant galaxies, scientists can start to piece together the history of our universe, how galaxies formed, evolved, and interacted over billions of years. Each new advance in technology doesn't just enhance our tools, it enriches our understanding of the cosmos, continually expanding our knowledge about not just what exists in the universe, but how the universe itself works. Rovers and landers are crucial instruments in our quest to understand planetary environments, particularly on Mars and beyond. These mobile and stationary vehicles allow scientists to collect data directly from the surface of distant worlds, revealing secrets that orbiters cannot as easily unveil. While orbiters can offer comprehensive views from space, It is the rovers and landers that engage intimately with the terrain, analyzing rocks, soil, and atmospheric conditions right where they lie. On Mars, for instance, rovers like Curiosity and Perseverance are equipped with sophisticated instruments to conduct experiments and capture images of their surroundings. They roam the Martian landscape, traversing hills, valleys, and ancient riverbeds, collecting samples and relaying vital information back to Earth. Each mission uncovers new details about the planet's geology and climate, improving our understanding of its past and its potential to support life. These rovers serve as mobile laboratories, able to conduct on-the-spot tests that reveal the composition of Martian materials. Lander missions, such as the InSight lander, provide another layer of exploration. By staying stationary, they can focus on specific scientific tasks like studying Marsquakes and measuring heat flow from the planet's interior. This information helps scientists piece together the history and structure of Mars, shedding light on not just its geology, but also its ability to sustain life in the distant past. The synergy between rovers and landers enriches our understanding, as they each bring unique capabilities to the table. Looking beyond Mars, landers and rovers are being planned for missions to icy moons like Europa and Enceladus, as well as to asteroids and comets. Each of these destinations presents unique challenges and opportunities for discovery. By constructing robotic explorers designed for varied environments, scientists hope to uncover the compositions of these celestial bodies and gather insights that could indicate habitability or even the existence of life. The role of these vehicles in our exploration of the solar system continues to expand, igniting curiosity and opening doors to unimaginable discoveries. The James Webb Space Telescope, often referred to as Webb, represents a monumental leap forward in our understanding of the cosmos. Launched in late 2021, its primary goal is to study the universe in unprecedented detail, particularly focusing on the infrared spectrum. This capability allows Webb to penetrate through dust clouds that obscure much of the light emitted by celestial objects, revealing the hidden processes of star formation, the atmospheres of exoplanets, and the earliest galaxies formed after the Big Bang. One of the most exciting prospects of the James Webb Space Telescope is its potential to explore the atmospheres of distant planets. By analyzing the light that passes through a planet's atmosphere as it transits in front of its star, Webb can identify the presence of various molecules, such as water, carbon dioxide, and even signs of potential habitability. This not only expands our search for life beyond Earth, but also deepens our understanding of planetary systems and their formation. Webb will also provide insights into the age and evolution of the universe. By looking back at light that has traveled for billions of years, it will help astronomers study the conditions of the early universe, specifically how stars and galaxies formed. This venture is critical for piecing together the history of the cosmos and understanding how our own galaxy, the Milky Way, fits into the broader story of the universe. Lastly, Webb is equipped with advanced technologies that will enhance observational capabilities, allowing scientists to gather data that was previously beyond reach. Its large mirror and sensitive instruments mean we can study fainter and more distant objects. As a result, Webb is poised to potentially answer some of the most profound questions about our universe, including the very nature of dark matter and dark energy, which together constitute most of the cosmos, yet remain largely enigmatic. The exploration of the outer planets and their moons holds a treasure trove of potential discoveries that could significantly reshape our understanding of the universe. Scientists are particularly curious about the gas giants like Jupiter and Saturn, along with their diverse moons. These moons harbor environments that may offer unique insights into the processes that govern planetary formation and evolution. For instance, the strong magnetic fields and vast atmospheres of these planets can reveal clues about their history, composition, and even the origins of life. One of the most exciting prospects lies with moons such as Europa, which is covered in a thick layer of ice, beneath which scientists believe there exists a vast ocean of liquid water. This raises tantalizing possibilities about the potential for life beyond Earth. Would these hidden oceans host microbial organisms? Or could complex ecosystems flourish beneath the ice? Exploring Europa could provide the first evidence of life elsewhere in the solar system, fundamentally changing our perspective on life's existence. Similarly, Saturn's largest moon, Titan, presents another fascinating area for discovery. Titan has a dense atmosphere and rivers and lakes of liquid methane and ethane on its surface. The chemistry happening there is unlike anything found on Earth and could lend insights into the processes of prebiotic chemistry. That is, how the ingredients for life might come together under different conditions. Studying Titan could open new doors in our understanding of atmospheres, climate, and possibly even the chemical pathways that lead to life. Moreover, missions to the outer planets could greatly enhance our knowledge of the solar system's formation. Understanding the dynamics and characteristics of these distant worlds could inform us about the early solar system, including materials that contributed to the Earth's development. Each discovery made in this remote part of our solar system not only adds to the grand narrative of planetary science, but also sparks new questions, inviting generations of scientists and enthusiasts to explore even further. The concept of parallel universes, often referred to as the multiverse, is a fascinating area of cosmology that has captured the imagination of both scientists and the general public. While many aspects of this idea are still theoretical, a few lines of evidence and reasoning suggest that parallel universes could exist. One significant support for this idea comes from the theory of cosmic inflation, which proposes that shortly after the Big Bang, our universe underwent an exponential expansion. This rapid growth could mean that distant regions of space, perhaps forever unobservable to us, contain their own unique universes, each with different physical laws and constants. Another intriguing piece of evidence is found in the peculiar fine-tuning of the universe. The specific values of fundamental constants, like the strength of gravity, seem almost too perfect to allow for the existence of life as we know it. Some scientists argue that if multiple universes exist, each could have varied constants and laws. Our universe just happens to be one of those rare instances that allows for the emergence of consciousness and complexity. This line of reasoning not only suggests the existence of parallel universes, but also serves as a potential explanation for the remarkable harmony we perceive in nature. Detecting parallel universes remains an enormous challenge. Unlike stars or planets, these alternate realities may not directly interact with our universe in measurable ways. However, researchers have proposed some fascinating approaches. One potential method is through studying the cosmic microwave background radiation, the afterglow of the Big Bang. Patterns or anomalies in this radiation might hint at interactions or collisions with other universes, providing an indirect glimpse into their existence. Additionally, mathematical frameworks such as string theory or quantum mechanics introduce concepts like branching timelines or ever-expanding planes of existence. These lend credence to the notion of parallel universes. Although we are not yet equipped to confirm their presence, the exploration of these ideas pushes the frontiers of science, continually inviting both research and philosophical inquiry into what lies beyond our visible reality. The timeline of the universe's evolution is a staggering narrative that unfolds over billions of years, and it offers both enlightening insights and challenges to existing theories. Our universe is thought to have originated from a singularity in what we call the Big Bang, occurring around 13.8 billion years ago. From that monumental moment, the universe has been expanding and evolving ever since. However, as we delve deeper into this cosmic timeline, we find emerging evidence that sometimes deviates from established theories, provoking thought and further investigation. For instance, the discovery of cosmic microwave background radiation validated the Big Bang theory, painting a picture of a hot, dense early universe. Yet, recent findings concerning the rate of expansion of the universe have raised eyebrows among scientists. Observations of distant supernovae suggest that this expansion is occurring at an accelerating pace, a phenomenon that has yet to be fully explained. This revelation introduces the concept of dark energy, a mysterious force that is thought to make up about 70% of the total energy content in the universe, yet its precise nature remains elusive. Additionally, the timeline reveals complexities in the formation of the first galaxies and stars. Initially, scientists believed that galaxies formed much later than they actually did. Recent observations using advanced telescopes have uncovered evidence of star formation much earlier than previously thought, leading researchers to reconsider their models of galaxy evolution. This challenges the notion of a linear progression, encouraging scientists to explore new theories that may better account for these early developments. As our tools and methods become more sophisticated, the cosmos continues to surprise us. Each new discovery about the universe's timeline not only enriches our understanding, but also challenges us to rethink our assumptions about the nature of the universe and its evolution. This ongoing dialogue between observation and theory remains a fundamental part of the scientific journey, reminding us that the quest for knowledge is as vast and dynamic as the universe itself. The cosmic microwave background, or CMB, is a relic radiation left over from the early universe, specifically from a time just after the Big Bang. This faint glow fills the universe and carries valuable information about its origins, structure, and evolution. When scientists study anomalies in the CMB, they focus on unexpected patterns or variations that might reveal new insights about the universe. One intriguing aspect of these anomalies is that they can hint at phenomena beyond our current understanding of physics. For instance, some anomalies may suggest that there are structures in the universe, like large voids or unexpected clumps of matter, which challenge our traditional models of cosmology. These findings can lead researchers to reevaluate their theories about the distribution of matter and energy, prompting new questions about the fundamental forces at play in the universe. Moreover, anomalies in the CMB can provide clues about possible new physics, potentially hinting at concepts like inflation or the existence of other dimensions. Inflation is a rapid expansion of space that is thought to have occurred just after the Big Bang. If anomalies can be linked to this process, they can offer insights into how the universe expanded, determining its large-scale structure today. In addition, studying these irregularities can help scientists refine their understanding of dark matter and dark energy, the mysterious components that make up most of the universe. As researchers continue to analyze these anomalies, they piece together a grander picture of the cosmos, revealing its complexity and the fundamental laws that govern it, ultimately deepening our understanding of existence itself. The quest to understand dark energy is one of the most exciting adventures in cosmology today. Dark energy, which makes up about 70% of the universe, is a mysterious force thought to be responsible for the accelerated expansion of the cosmos. This discovery has upended our traditional models of the universe, leading scientists to rethink the fundamental principles of space, time, and gravity. When astronomers observed distant galaxies, they found that instead of slowing down, the universe's expansion is speeding up. This unexpected revelation has pushed theorists to develop new models that incorporate dark energy. For years, the prevailing sentiment was that gravity, which pulls objects together, would eventually lead to a slowing down of the universe's expansion. However, with dark energy in the picture, we must consider a repulsive force that counters gravity's pull on larger scales, changing how we perceive the universe's fate. As we delve deeper, scientists explore various theories to explain dark energy. Some suggest that it may be a property of space itself, leading to the idea that the universe potentially expands forever. Others propose alternatives, such as modifications to Einstein's theory of gravity, or the possibility of dynamic fields that could change over time. Each hypothesis not only sheds light on dark energy, but also reshapes our understanding of fundamental cosmic forces. The ongoing study of dark energy holds profound implications for our understanding of the universe. As new observations arise and theoretical models evolve, cosmologists are challenged to rethink their frameworks. This vibrant interplay between observation and theory is a hallmark of scientific progress, pushing the boundaries of our knowledge and deepening our appreciation for the cosmos in which we live. The quest for understanding dark energy is not just an academic pursuit, it is a journey into the very nature of reality itself. Cosmic rays, those mysterious particles constantly bombarding Earth from outer space, have led to some groundbreaking discoveries that reshape our understanding of the universe. These high-energy particles, mainly protons but also heavier nuclei and electrons, originate from distant astrophysical events such as supernova explosions, active galactic nuclei, and even the remnants of cosmic rays from beyond our galaxy. As they travel through space, they can carry clues about their origins, providing unique insights into the processes occurring in the universe. One striking discovery is the role cosmic rays play in the formation of new particles and elements in our atmosphere. When these high-energy particles collide with molecules in the air, they create secondary particles, which can lead to a cascade of events that contribute to atmospheric chemistry. This interaction can also influence cloud formation and, indirectly, our climate. Understanding these effects emphasizes the interconnectedness of cosmic phenomena and life on Earth, reminding us that even the most distant events can have a direct impact on our planet. Furthermore, scientific advancements in detecting these particles have opened new windows into astroparticle physics. For example, observatories such as the Pierre-Auger Observatory and the Ice Cube Neutrino Observatory have made significant strides in capturing and studying cosmic rays. These facilities enable scientists to analyze their energy levels and trajectories, guiding our comprehension of extreme cosmic events and the conditions under which they occur. This research extends beyond mere curiosity, impacting our understanding of fundamental physics and the very fabric of the universe. Lastly, the debate surrounding the possible sources of ultra-high-energy cosmic rays, those with energies surpassing what can be produced in terrestrial laboratories, continues to deepen our knowledge. The challenge of identifying their origins underscores a fundamental question. Are they triggers for new realms of physics? Each discovery in cosmic rays not only unravels the mysteries of the universe, but also propels forward our understanding of the most extreme conditions imaginable. This ongoing investigation into the cosmos serves as a reminder of our place within an ever-expanding universe filled with wonders yet to be understood. Extremophiles are remarkable microorganisms that thrive in some of the most inhospitable environments on Earth. These tiny life forms can be found in places like deep-sea hydrothermal vents, powerful acid lakes, and even within ice in Antarctica. Their resilience to extreme temperatures, pressures, and salinity provides crucial insights into how life can exist in similarly harsh conditions elsewhere in the universe. Studying these organisms helps scientists understand the biochemical adaptations that allow life to persist under such extreme circumstances. For instance, certain extremophiles employ unique enzymes that remain functional at high temperatures, while others possess cell membranes that withstand intense acidity. These adaptations not only reveal the limits of life on our own planet, but also suggest that similar forms of life could potentially thrive on celestial bodies like Mars or the icy moons of Jupiter and Saturn, where extreme conditions might exist. Moreover, the environments where extremophiles flourish often resemble extraterrestrial settings. For example, the salty lakes and craters on Earth bear a striking resemblance to conditions scientists find on Mars. This parallel fuels the idea that if life can endure on Earth in such extreme niches, it may also be present elsewhere, perhaps lurking beneath the surface of ice-covered oceans or in the soil of barren planets. By continuing to explore and understand extremophiles, we not only expand our knowledge of life's diversity here on Earth, but also enhance our ability to identify potentially habitable environments beyond our planet. This exciting field of research serves as a profound reminder of life's tenacity and the endless possibilities that may lie in the cosmos. The search for microbial life on Mars captivates scientists for several compelling reasons. Firstly, Mars is often described as Earth's closest neighbor in our pursuit of understanding life beyond our planet. With its similar day length, polar ice caps, and past presence of liquid water, Mars presents an intriguing possibility for ancient microbial life. The idea that life might have existed on Mars billions of years ago inspires scientists to explore the planet's surface and subsurface for traces of microorganisms. Furthermore, Mars has shown evidence of conditions suitable for life in the past, such as riverbeds and minerals that typically form in the presence of water. This historical journey through its climate reveals a planet that was once potentially warm and wet, contrasting sharply with its current cold, desert-like state. The potential discovery of microbial life could illuminate how life might evolve in diverse environments, thus expanding our understanding of biology and ecology across the cosmos. Additionally, understanding microbial life on Mars could provide insights into the resilience of life forms. If microbial life once thrived on Mars, it raises fascinating questions about how organisms adapt to harsh conditions. Such knowledge not only fuels our curiosity about Martian life, but also informs our understanding of extremophiles, organisms on Earth that survive in extreme environments, from deep-sea vents to polar ice. As scientists delve into Mars's geological and atmospheric history, the prospect of finding microbial fossils, biosignatures, or even living organisms ignites a profound quest for knowledge. This journey is not just about discovering life. It challenges our perceptions of where life can exist and inspires hope for future explorations beyond our planet, perhaps revealing that we are not alone in the universe. Recent discoveries have sparked excitement in the search for life beyond our Earth, particularly on exoplanets, which are planets orbiting stars outside our solar system. One significant area of study is the detection of atmospheres around these distant worlds. Scientists have observed promising chemical signatures, such as oxygen and methane, which on Earth are often produced by biological processes. The juxtaposition of these gases suggests that, at least theoretically, a similar process could be occurring on these exoplanets. To evaluate the potential for life on these distant worlds, scientists rely on advanced telescopes equipped with spectrometers. When light from a star passes through an exoplanet's atmosphere during a transit, it leaves a unique fingerprint. This fingerprint allows scientists to analyze the composition of the atmosphere and determine the presence of key molecules that could indicate habitability. Chemists have identified several criteria that may signify a planet's ability to support life, such as the presence of liquid water, a stable temperature range, and the right atmospheric conditions. One particularly intriguing finding came from the observations of a planet known as Kepler 186f, located in the habitable zone of its star, where conditions might allow for liquid water. The atmosphere of this planet has not yet been fully characterized, but the mere potential for such an environment has incited curiosity. In addition, the recently launched James Webb Space Telescope is anticipated to provide deeper insight into these atmospheres, offering astronomers the ability to analyze previously uncharted territory. The exploration of exoplanets remains an evolving field, with new discoveries constantly reshaping our understanding. As we gather more data, scientists continue to refine their methods of evaluating habitability, turning the dream of discovering extraterrestrial life into an achievable goal within our lifetime. The thrill of potentially finding life on another planet beckons, highlighting the vast complexities and wonders of our universe. Future missions to ocean worlds like Europa and Enceladus hold the potential to profoundly reshape our understanding of life beyond Earth. These icy moons of Jupiter and Saturn, respectively, are intriguing because they possess subsurface oceans beneath their frozen crusts. Scientists believe that these oceans could harbor the essential ingredients for life, such as water, organic compounds, and energy sources. By exploring these celestial bodies, we may find direct evidence of microbial life, or at least the conditions that could support it. Both Europa and Enceladus have already shown signs that they are geologically active. Enceladus has impressive geysers that shoot plumes of water vapor and ice particles into space, while Europa's surface is crisscrossed by cracks, hinting at a dynamic ocean underneath. Future missions could employ advanced technology to analyze these plumes, or even send landers to the surface. Such explorations could reveal more about the chemical makeup and potentially habitable conditions of these environments, providing clues about how life can exist in extreme conditions. The implications of discovering life, or even just the potential for it, could be monumental. It would challenge our understanding of where and how life can thrive, suggesting that life isn't limited to planets within the so-called Goldilocks zone, where conditions are just right for liquid water. Instead, it could exist in surprising places with extreme pressures and cold temperatures, expanding the cosmic possibilities of life's existence. Moreover, exploring these ocean worlds might lead to questions about our own place in the universe. Would we be willing to share our understanding of life with entirely alien ecosystems? What would we learn about evolution, adaptation, and the universal conditions that create life? Each mission promises to peel back another layer of mystery, urging us to reconsider not just where life might exist, but what it truly means to be alive in the cosmos. Astrobiology is a fascinating field that explores the potential for life beyond Earth. It serves as a bridge between biology, astronomy, and planetary science, working to understand the conditions under which life could arise and thrive elsewhere in the universe. The underlying question driving astrobiology is simple yet profound. Are we alone in the cosmos? This inquiry has led scientists to consider a variety of environments, from the icy moons of Jupiter and Saturn to distant exoplanets swirling around other stars. The role of astrobiology extends beyond merely searching for life. It involves understanding what life is and how it could survive in different conditions. Researchers study extremophiles, organisms that exist in extreme environments on Earth, such as deep-sea vents or acidic lakes. By examining how these resilient life forms adapt, scientists gain insight into the possibilities for life in similarly harsh conditions elsewhere. This knowledge helps to shape our expectations and defines the criteria for what constitutes a potentially habitable environment in space. In addition to looking at where life might exist, astrobiology also examines the biosignatures that indicate life. These are chemical indicators or patterns that scientists could detect from afar. For example, the presence of oxygen alongside methane in a planet's atmosphere could signal biological processes. The search for biosignatures plays a critical role in missions aimed at Mars or the exploration of distant exoplanets, guiding the instruments and techniques used to analyze their atmospheres and surfaces. Ultimately, astrobiology not only informs our search for extraterrestrial life, but also deepens our understanding of life on Earth itself. By studying the origins, evolution, and future of life, we can appreciate the unique conditions that allow life to flourish. This inquiry enhances our perspective on our place in the universe, sparking both scientific discovery and a sense of wonder about the potential for life beyond our home planet. Throughout history, cosmic imagery has played a profound role in art, serving as both inspiration and a reflection of humanity's quest to understand the universe. From ancient civilizations gazing up at the stars and charting the movements of celestial bodies, to modern artists experimenting with cosmic themes, the night sky has been a canvas for expressing the mysteries of existence. The interplay of light and darkness, the vastness of space, and the beauty of celestial objects have allowed artists to explore concepts such as infinity, time, and the unknown. In many cultures, celestial themes have been intertwined with mythology and spirituality. For example, the ancient Greeks depicted constellations as figures from their mythology, merging the divine with the astronomical. These artworks serve to anchor human experience in a broader cosmic context, illustrating how people have historically connected their earthly lives with the heavens. This connection often evokes feelings of wonder, awe, and a sense of belonging in a much larger narrative. As we moved into the Renaissance, artists like Leonardo da Vinci and artists of the Baroque period began incorporating more scientific understandings into their works. They attempted to capture the beauty of the night sky and the complexity of cosmic phenomena, reflecting the era's growing interest in both science and philosophy. This transition illustrates how art can serve as a bridge between human emotion and the scientific exploration of the universe, encouraging viewers to ponder their own place in the cosmos. Today, contemporary art continues to delve into cosmic themes, often using cutting-edge technology and digital media to represent the universe's vastness. Artists explore both the beauty and the terrifying scale of the cosmos, prompting modern viewers to reflect on existential questions. What does it mean to be human in the grand scheme of the universe? Cosmic imagery remains a powerful conduit for expressing our deepest fears, hopes, and dreams, making it an enduring aspect of our artistic narrative. Science fiction has always been a powerful medium in shaping our perceptions of space and its myriad mysteries. The imaginative landscapes created by authors and filmmakers stretch the boundaries of our understanding, inviting us to ponder the unknown. From the epic tales of distant galaxies to the exploration of alien life, science fiction serves not only as entertainment, but also as a catalyst for curiosity and discussion about what lies beyond our atmosphere. These narratives often introduce themes and ideas that gradually seep into the public consciousness. For instance, concepts such as advanced technology, time travel, and extraterrestrial civilizations spark conversations about the possibilities of actual scientific advancements. When films and books portray robust space exploration missions or the discovery of intelligent life, they plant seeds of wonder and excitement. This can lead to increased public support for space exploration efforts, inspiring generations to pursue careers in science and engineering. Moreover, science fiction often reflects our societal values and concerns about technology, ethics, and the environment. For example, stories that explore the consequences of colonizing new worlds prompt us to question our impact on Earth. They challenge us to think critically about resource consumption, sustainability, and our responsibilities as stewards of our planet. This reflection can drive public discourse, influencing policy decisions and how we approach emerging scientific challenges. In many ways, science fiction not only entertains, but educates. It can demystify complex scientific principles by wrapping them in a narrative that captivates the imagination. As audiences engage with these stories, they develop a sense of wonder about the universe and our place in it, sparking a desire for knowledge and understanding that extends far beyond the pages of a book or the screen of a movie. Through engaging storytelling, science fiction continues to shape how we perceive space and encourages us to explore the questions that remain unanswered. Cosmic themes have long inspired storytellers in both theatre and cinema, captivating audiences with their vastness and mystery. The night sky, filled with swirling galaxies, shimmering stars, and unknown possibilities, often serves as a backdrop for exploring fundamental human questions about existence, purpose, and the universe itself. Filmmakers and playwrights find in the cosmos a canvas that transcends everyday experiences, inviting characters and audiences alike to embark on journeys that provoke introspection and wonder. In many narratives, the cosmos serves as a symbol of the unknown, representing both the fears and aspirations inherent in the human condition. Movies like Interstellar and plays such as The Tempest utilize celestial elements to portray characters facing monumental challenges that reflect their inner struggles. For instance, in Interstellar, the vastness of space becomes a metaphor for love and sacrifice, while The Tempest employs the supernatural to explore themes of power and redemption. Such stories draw audiences into a dialogue about humanity's role in the universe, blurring the lines between enlightenment and despair. The visual appeal of cosmic landscapes also sparks creativity, leading to imaginative storytelling techniques. In film, the grandiosity of black holes, supernovae, and distant worlds can be rendered with stunning special effects, providing a feast for the eyes that enhances the plot. The experience of watching a film can become almost transcendent, as audiences gaze upon the magnificence of a star-filled sky or the swirling colors of a nebula, igniting their sense of wonder. Theatre too embraces innovative staging and lighting to evoke the vastness of the universe, elevating the narrative experience. In conclusion, cosmic themes resonate deeply because they tap into the universal intrigue surrounding our place in the larger tapestry of existence. Whether through dramatic monologues or breathtaking visuals, the cosmos continues to inspire artists to explore the profound questions that define our humanity. As we gaze up at the stars, we cannot help but wonder, are we alone in this vast universe? And what does it mean to be part of something so magnificent? These questions remain at the heart of storytelling, drawing audiences closer to both the cosmos and each other. When it comes to exploring the mysteries of the cosmos, literature offers a unique lens through which to understand our universe. One standout work is Cosmos by Carl Sagan, which marries science with lyrical prose. Sagan takes readers on a journey through the universe while delving into the origins of life and human consciousness. His ability to narrate complex scientific concepts in an accessible and engaging manner has made Cosmos a beloved classic, inviting readers to marvel at the vastness and intricacies of existence. Another significant title is Gravity's Rainbow by Thomas Pynchon. Although primarily a novel about World War II and the development of the V-2 rocket, it dives deep into themes of entropy and gravitational forces as metaphors for the chaotic nature of life. Pynchon's intricate storytelling intertwines scientific principles with philosophical questions, pushing readers to reflect on humanity's struggle against the forces that govern both the world and the cosmos. The Three-Body Problem by Liu Cixin offers a thrilling exploration of physics and the potential existence of extraterrestrial civilizations. This award-winning science fiction novel delves into first contact with an alien species, interspersed with real scientific theories related to astrophysics and the behavior of complex systems. Its blend of hard science fiction and profound existential questions has captivated readers, encouraging them to ponder the implications of our place in the universe. Lastly, there's The Dispossessed by Ursula K. Le Guin, which from its very title suggests a conversation about belonging and perspective. While it's fundamentally a story about societies, it draws comparisons between differing worlds and cultures, highlighting how the cosmos serves as the backdrop for our most profound philosophical inquiries. Le Guin's work invites readers to contemplate the realities of existence beyond our planet and reflects on what it means to be part of something much larger than ourselves. Through these literary works, the mysteries of the cosmos become accessible, inspiring both wonder and inquiry in those who dare to explore them. Creativity plays a vital role in scientific exploration, especially when it comes to understanding the universe. At its heart, science thrives on imagination. It enables scientists to pose questions about the cosmos that go beyond what is currently known. For instance, concepts like black holes or dark matter were born from creative thinking, initiated by observations that defied conventional explanations. These ideas challenge our perceptions and encourage us to explore scenarios that might initially seem improbable. Think about how the human mind works. It craves patterns and narratives to make sense of the vastness around us. Scientific models, which attempt to describe the complex behaviors of celestial bodies, rely heavily on metaphor and analogy. For example, the idea of the expanding universe is often depicted as a balloon inflating with dots on its surface representing galaxies. This image resonates deeply because it allows us to visualize complicated processes that are otherwise abstract, merging creative visual thinking with scientific principles. Furthermore, artistic expression often serves as a medium for communicating complex scientific ideas. Movies like Interstellar depict scientific concepts such as time dilation and gravity with stunning visual flair. This not only captivates an audience but also distills essentially dense ideas, making them accessible to a broader public. The intersection of arts and science can inspire new ways of thinking, encourage collaboration, and even lead to groundbreaking discoveries. Finally, creativity and exploration extends to the technology scientists use to probe the cosmos. Innovations in telescopes, satellites, and space probes are products of imaginative engineering. Each new tool provides fresh opportunities to observe and understand phenomena that lie beyond our reach, pushing the boundaries of our knowledge. Thus, creativity is not just an aspect of scientific inquiry, it is a fundamental driving force that shapes our quest to unravel the mysteries of the universe. As we look ahead, both ground-based and space-based astronomy are poised for remarkable advancements that promise to deepen our understanding of the universe. Ground-based observatories are beginning to employ adaptive optics technology, a method that corrects for the blurring effects of Earth's atmosphere. This breakthrough allows astronomers to obtain clearer images of celestial objects. Additionally, the development of extremely large telescopes, such as the Gran Telescopio Canarias, with mirrors over 30 meters across, will significantly enhance our ability to observe faint and distant galaxies. In space, the use of artificial intelligence in astronomy is on the rise. This technology can sift through vast amounts of data at remarkable speeds, helping scientists identify patterns and anomalies that would take humans much longer to spot. For example, AI is already helping in the search for gravitational waves and in classifying different types of astronomical events, enhancing our knowledge of the universe's dynamics. As these technologies mature, they will not only broaden our understanding of cosmic events, but also allow for collaborative research on a global scale. With international partnerships forming between space agencies and universities, we can expect a renaissance in astronomical discoveries. These advancements will undoubtedly captivate our imaginations and challenge our perceptions of the universe we inhabit. Establishing a moon base could serve as a significant stepping stone for further exploration of our solar system. The moon, being relatively close to Earth, offers a unique opportunity for scientists and astronauts to develop and test the technologies needed for long-duration space missions. This base could act as a launching point for future missions to Mars and beyond, providing a less gravitationally demanding environment from which spacecraft can be launched with reduced fuel requirements. Additionally, a lunar base would facilitate ongoing research that can only be conducted off Earth. The moon's surface conditions, like its lower gravity and lack of atmosphere, make it an ideal place for studying the effects of space on human physiology and the performance of equipment. Test missions on the moon could yield invaluable data on how life might survive on other planets, making a significant impact on long-term plans for human habitation beyond our planet. The moon also holds untapped resources, such as water ice in permanently shadowed craters, and materials like helium-3 that could potentially be used in fusion energy. Establishing a sustainable lunar base would not only allow for the extraction and utilization of these resources, but also foster international collaboration, as countries come together to share knowledge and expertise in this new frontier. Such cooperative efforts have the potential to unify humanity around a common goal and push the boundaries of what is possible in space exploration. Ultimately, a moon base would ensure that humanity is not just taking tentative steps into space, but is laying a solid foundation for the next era of exploration. By extending our presence beyond Earth, we open the door to an exciting future where missions to Mars and other celestial bodies become not just dreams, but achievable realities. International collaboration in cosmic research opens up a universe of potential advantages. When countries come together, they combine their resources, knowledge, and expertise. This not only leads to efficiencies in funding and technology, but also enhances the breadth of scientific inquiry. Each nation contributes its unique perspectives and methodologies, often resulting in a richer, more holistic understanding of cosmic phenomena. Moreover, collaborative projects often attract a diverse group of scientists and researchers. This melting pot of backgrounds fosters innovation and creativity, leading to breakthroughs that might not be possible in isolated environments. For example, the construction of powerful telescopes, such as the Event Horizon Telescope, required the combined efforts of scientists from around the globe, allowing them to capture the first image of a black hole. One major advantage of collaboration is the sharing of data and findings. Space is vast, and the challenges of exploring it are immense. By pooling resources and sharing findings, researchers can accelerate the pace of discovery. Imagine the speed with which we could unlock the secrets of black holes or explore the far reaches of our galaxy if countries work together, sharing both triumphs and setbacks openly. Lastly, international collaboration can inspire public interest and support for scientific endeavors. When people see scientists from different cultures working hand in hand towards a common goal, it fosters a sense of unity and shared purpose, captivating the imagination of future generations. This collaborative spirit not only propels scientific advancement, but also strengthens the human connection to the cosmos, reminding us that we are all part of something much larger than ourselves. Public interest in space exploration plays a significant role in shaping funding and research priorities. When citizens become captivated by the cosmos, they often express their enthusiasm in various ways, such as through social media engagement, public events, and grassroots movements. This collective interest can influence government agencies and private organizations, encouraging them to allocate more resources towards space missions, science education, and technological advancements. For example, when spectacular events occur, such as a successful Mars landing or the unveiling of groundbreaking telescopes, the thrill of discovery can spark widespread excitement. This fervor often translates into greater visibility for space programs and can prompt policymakers to advocate for increased funding. Ultimately, when people show a keen interest in what lies beyond our planet, it can shift budget priorities, ensuring that space exploration remains at the forefront of scientific endeavors. Moreover, private companies are also attuned to public fascination with space. Organizations like SpaceX and Blue Origin have tapped into this enthusiasm, using it to fuel investments and drive innovation. Crowdfunding campaigns and public conferences can gauge interest and directly influence the direction of research initiatives, enabling projects that resonate with the public psyche. However, it is essential to understand that this public enthusiasm is not just a matter of funding. It also shapes the types of missions pursued and the areas emphasized, such as planetary exploration, the search for extraterrestrial life, or the impact of space on Earth's climate. As people's fascination with outer space evolves, so too will the landscape of funding and research priorities, creating a dynamic interplay between scientific ambition and public imagination. Artificial intelligence and machine learning have emerged as powerful tools in the quest to unravel the mysteries of the cosmos. These technologies are particularly adept at processing immense amounts of data, a task that has become essential in modern astronomy, where telescopes and satellites generate terabytes of information daily. By automating the analysis of this data, AI can help scientists identify patterns and anomalies that might otherwise go unnoticed. One of the most significant contributions of AI is in the realm of image recognition. Whether it's analyzing the vast swathes of the night sky captured by a telescope or processing signals from distant cosmic events, machine learning algorithms can quickly sort through images, pinpointing celestial objects and even detecting new ones. For instance, researchers have employed AI to discover thousands of new exoplanets by analyzing light curves, subtle changes in brightness caused by planets transiting in front of their stars. Furthermore, AI can assist in simulating complex astrophysical processes, such as galaxy formation or black hole mergers. These simulations require enormous computational power and intricate modeling. Machine learning can optimize these processes by predicting outcomes based on existing data, effectively helping physicists understand phenomena that have eluded them for decades. This predictive capability could lead to groundbreaking discoveries, reshaping our understanding of the universe. As we continue to explore deeper into the cosmos, the integration of AI and machine learning is expected to accelerate our pace of discovery. These technologies might not only enhance our analytical capacity, but also inspire new questions and hypotheses about the universe. In this way, AI is not just a tool, but a collaborator in the age-old human endeavor of searching for knowledge among the stars. Current and future space telescopes are poised to revolutionize our understanding of the universe in profound ways. Over the past few decades, telescopes like Hubble have already unveiled a treasure trove of information about distant galaxies, nebulae, and stars. However, new instruments such as the James Webb Space Telescope are set to exceed those milestones by allowing us to peer deeper into the cosmos. With their advanced technology, these telescopes can capture light from some of the first galaxies that formed after the Big Bang, providing us with fresh insights into the nature of the early universe. One of the most exciting prospects is the ability to study exoplanets, which are planets beyond our solar system. Future observations will enable scientists to analyze their atmospheres in unprecedented detail. This could help identify planets that have conditions suitable for life, enhancing our understanding of where life might exist in the cosmos. With the careful study of these distant worlds, we could discover a diverse array of planetary systems and perhaps even traces of biological activity. Moreover, space telescopes are also set to shed light on dark matter and dark energy, two of the biggest mysteries in cosmology. By observing gravitational influences and the expansion of the universe, they will provide data that could explain how these elusive components shape the cosmos. Understanding these phenomena is crucial, as they account for the vast majority of the universe's mass energy content, yet remain poorly understood. As we gather more data from these advanced telescopes, our models of the universe will have to adapt. Each new discovery could challenge existing theories or spark entirely new lines of inquiry. As our technologies advance, so too will our comprehension of not just the cosmos, but our own place within it, opening the door to a deeper understanding of the fundamental laws that govern the universe. The exploration of Mars and other celestial bodies is poised to have profound and lasting impacts on our understanding of the universe and our place within it. As humanity strives to reach Mars, we are not simply focused on the mission itself, but also on what we might learn about planetary formation, climate, and the possibilities for life beyond Earth. Discovering whether life ever existed on Mars could reshape our understanding of biology, evolution, and the conditions necessary for life to thrive. Moreover, the technologies developed for space exploration often find applications here on Earth. For instance, advancements in materials, science, robotics, and telecommunications have all been spurred by the challenges of distant travel. These innovations frequently trickle down to various industries, improving everything from medical devices to environmental monitoring. As we venture further into our solar system, the engineering and scientific challenges faced will yield insights and tools that enhance everyday life on our planet. Culturally, the exploration of Mars and beyond ignites the imagination and inspires future generations. It serves as a powerful reminder of human ingenuity and our quest for knowledge. Children today, fascinated by stories of astronauts and space missions, may one day become the scientists, engineers, and explorers who take us further into the cosmos. This intergenerational transfer of inspiration could lead to a renewed interest in STEM fields, science, technology, engineering, and mathematics, fostering a workforce capable of tackling the grand challenges of our time. Finally, the ongoing quest to understand the universe encourages a sense of shared responsibility for our own planet. As we learn more about the potential for colonization and resource utilization on other celestial bodies, the significance of sustainability on Earth becomes even clearer. The knowledge that we are part of a larger cosmic community may inspire more profound respect and a holistic approach to how we care for our planet, ultimately leading to a more unified and conscious effort in the stewardship of Earth. As humanity embarks on its continued journey into space, the impact on future generations will be profound and multifaceted. Space exploration, at its core, symbolizes the relentless human spirit of curiosity and discovery. It inspires new generations to look beyond the confines of our planet, igniting a sense of adventure that can shape their aspirations and careers. As we venture into realms once thought unreachable, children growing up in this age are likely to view the cosmos not just as a background, but as their potential playground. One of the most exciting aspects of space exploration is the technological advancements it fuels. Often, innovations developed for space missions trickle down to everyday life, leading to improvements in healthcare, communication, and transportation. For instance, technologies developed for space observation aid in understanding our own planet's climate and environmental challenges. Thus, the future generations may inherit a world transformed by the very tools devised for exploring outer space, equipping them to navigate the complexities of life in a more informed way. Moreover, the human journey in space raises essential questions about our identity and our responsibilities as a species. The sight of Earth from space, often described as a breathtaking blue marble suspended against a vast black backdrop, compels a deeper reflection on the fragility of our home. This perspective could foster a sense of global stewardship in future generations, encouraging them to care for our planet with the same vigor we devote to exploring the universe. As they become aware of the interconnectedness of all life on Earth, they may advocate for sustainability like never before. Lastly, the prospect of humanity becoming a multiplanetary species introduces bold and exciting possibilities. Colonizing other planets could reshape our understanding of survival, governance, and community. Future generations may grapple with what it means to be human on a broader scale, as they establish life elsewhere and forge new interstellar relationships. The journey into space may not only shape our scientific and technological landscape, but also redefine us spiritually and socially, allowing us to dream of a future that was once just the stuff of science fiction. The stories of cosmic exploration have a unique ability to deepen our appreciation for the natural world on Earth. When we look up at the night sky and behold the vastness of the universe, we are reminded of our own planet's delicate beauty and its remarkable position in the cosmos. For instance, images taken by telescopes like the Hubble Space Telescope show nebulae and distant galaxies that shimmer with colors and shapes we can scarcely imagine. These cosmic wonders illustrate the complex processes at play in the universe and connect us back to the elemental forces that shape our own planet. Moreover, the exploration of other celestial bodies offers a glimpse into the potential futures of our world. When scientists study Mars, for example, they examine signs of ancient water and climate change, providing lessons about Earth's own history and environmental challenges. Understanding that other planets have undergone dramatic transformations compels us to consider the fragility of our own atmosphere and ecosystems. It sparks a sense of stewardship for our home, urging us to cherish the biodiversity and natural resources that exist on our blue planet. Acts of cosmic discovery also highlight the intricate connections between all forms of life. The fact that the elements forming our bodies were forged in the hearts of ancient stars fosters a profound sense of unity with the universe. When we learn that the carbon, nitrogen, and oxygen crucial for life on Earth originated in cosmic events, it invites us to reflect on our place within this larger narrative. This cosmic perspective encourages us to see ourselves as part of a much grander story, one filled with interconnectedness and shared origins. Ultimately, the drama of the cosmos enhances our awareness of our environment. As we venture beyond Earth and send rovers to explore distant worlds or satellites to survey our own, we cultivate a greater respect for nature and the intricate systems that sustain life. Cosmic exploration ignites curiosity and broadens our horizons, reminding us that the beauty of Earth is not only unique, but also part of the larger tapestry of existence that unfolds throughout the universe. As we continue to explore the cosmos, the narrative of the universe is becoming richer and more intricate. With each new discovery, we are not just filling in blanks, but are also redefining the questions we ask. The story of the universe is not static. It grows with our understanding of fundamental concepts like space, time, and gravity, which have evolved from mere hypotheses into verified scientific principles. Each revelation peels back another layer of the cosmic onion, revealing deeper truths about the origins of galaxies, stars, and even the possibility of life beyond Earth. Recent advancements in technology, such as powerful telescopes and space probes, have allowed us to look deeper into the universe than ever before. For example, the James Webb Space Telescope is capturing exquisite images and data from distant galaxies, enabling scientists to study the very formation of stars and planetary systems. Each image brings new chapters to the story, such as evidence of the universe's accelerated expansion and mysterious dark energy. This deepening understanding leads us to consider profound philosophical questions about our place in the cosmos and the nature of reality itself. Additionally, the discovery of exoplanets, planets outside our solar system, has sparked immense interest in the hunt for life beyond Earth. As of now, thousands of these distant worlds have been identified, some in their star's habitable zone, where conditions might be just right for life as we know it. Each of these findings tantalizes us with the possibility that we may not be alone in the universe, weaving additional threads into the fabric of our cosmic narrative. Ultimately, the universe's story is one of exploration, inquiry, and continual revelation. As our tools improve and our insights grow, we not only uncover the mysteries of the universe but also reflect more deeply on our existence within this vast expanse. Each discovery challenges us to expand our imaginations, encouraging us to contemplate both the known and the unknown. The more we learn about the cosmos, the more curious we become, and that curiosity itself is a vital part of our shared human adventure.